Very good morning and warm welcome you all, the participants. As you know that the session expert Dr. Abhishek Singh from NIT Patna has already joined us. So he will deliver his talk. So before requesting Dr. Abhishek Singh, I would like to brief some about him and also to share some with the participants. Dr. Abhishek Singh is currently serving the Department of Mechanical Engineering with the capacity of Assistant Professor at NIT Patna. He did his PhD degree in the Department of Mechanical and Industrial Engineering at Indian Institute of Technology, Roorkee in 2014. He is also the member of seven societies and associations. His research areas are broadly related with the advanced and hybrid manufacturing processes, machining of advanced composite materials, the processings and characterization of the composite materials, metal composite, etc. He also served as a nodal officer and faculty advisor at NIT Patna. He has published more than 40 plus articles in the various journals at international and national levels. He has also published 25 international conferences so far. Uh, he also conducted three international conferences at different institutions. He is also the active member of various professional bodies. So there is more to share, Professor Abhishek. But because of the time constraint, I would like my request to extend my request to Dr. Abhishek. So please, Dr. Abhishek sir, it's now hand over to you, please.
Very good morning to all of you. Thank you very much for getting so well introduced, Dr. Ravi Pratap sir. It is my pleasure to be a part of this online FDP course. And thank you to coordinator and NIT Jalandhar for their tremendous support of this course. Okay, I hope
We welcome you, sir. We welcome you.
beneficial to all the participants. Okay. Uh, Sir, my PPT is visible.
Uh, yes, sir, it is completely visible, sir. Very clear.
Uh, I am here to present my lecture on advances in electrical discharge machining. So first, introduce the conventional, then go to non-conventional manufacturing process, then various branches of EDM process. The conventional machining process induce the material removal processes such as drilling, shaping, milling, and grinding. In the conventional machining process, the final shape of the product is obtained by removing extra materials with the help of cutting tools, and a result of this relative motions between cutting tools and the work materials. With the improvement of properties of the advanced material and developed processes and technology, more and more challenges and problem faced by the researcher or scientists in this area. The challenges in this field of the advanced manufacturing can be categorized in terms of maximum uh, maximum production rate, maximum production rate and economy. The second one is new materials, new materials with a low machinability. Okay. His third one is accuracy and dimensions requirement. Okay. The conventional machining process, with the innovation in this field of the advanced materials, composite materials are being developed worldwide, uh, in order to justify their usual mechanical, physical, and the chemical characterizations using conventional machining processes. The To machine hard metals or alloy means increases demand of time and energy, and therefore the increasing the cost. In some cases, the conventional machining process may not be feasible. Okay, the conventional machining process also cost efficiency of the tool, terms of the tool wear, and in loss of quality of the product, owing this introducing the residual stress during the manufacturing, with ever increasing the demand for the manufacturing goods of the hard alloy or metals such as inconel, titanium, and all those things. Okay, more interested as gravitated to non-conventional machining process. Therefore, the machining process to hard alloys or metals with the unconventional machining process, with the micro and micro electro discharge machining process, ultrasonic, it's become to an figure. Okay, so tool is in this machining process, conventional machining process is harder than the workpiece, but in non-conventional machining process is tool not harder than the workpiece materials, and no direct contact between the tool and workpiece. So there is a less wear or negligible wear as compared to unconventional machining process. Okay, there are clearly many issues and challenges with the conventional machining process or hole making process in the advanced materials. Okay, or developed material such as a metal matrix composite or inconel, etc. And these need to address if we aim to increasing the range of applications in the various type of materials. In this regard, with the innovation in this area of advanced material or hybrid machining materials, using the various unconventional machining process are being developed. Okay, the micro machining process are broadly classified as a traditional or advanced machining processes. This slides so the classification of micro machining process. Okay, but non-conventional machining process also calls divide into three major energy-based machining process. First part is the mechanical-based energy machining process. Second one is the thermal energy-based machining process, and third one is the chemical energy-based machining process. Next, the classified the hybridizations. What the mean of this hybrid terminology of the hybrid? The hybrid machining processes are defined as a combination of two and more than two machining process simultaneously. Okay, they combine various physical and the chemical processes acting the on the workpiece material into the one machining process. Okay, these hybrid machining process are developed to enhance the potential advantages and to minimize the disadvantage associated with a individual part. Okay, the this hybrid machining process, that is micro electro discharge, discharge, chemical grinding, electro discharge, hole grinding, micro powder mix electro discharge grinding, micro electro discharge phase grinding. Okay, basically the hybrid machining process can be classified or two parts. First is those processes in which or the constituent process are directly involved in the material remove, and secondly those processes in which only one of the participating processes directly remove the materials while other only assist in removal by the changing the condition of the machining. Okay, my entire lecture, which I have divided into the five categories. First part is electro discharge drilling, and second part is the electro discharge hole grinding, electro discharge, third one is the electro discharge sewing, and fourth one is the micro electro discharge machining, and fifth one is the powder mix micro electro discharge machining. Okay, here we start with the first part, electro discharge drilling. Okay, the electro discharge drilling and hole grinding is hybrid machining processes. Okay, the electro discharge drilling, sometimes called rotary EDM or discharge drilling process. Okay, as it's remove material by the producing a rapid series of a rapid series of the repetitive electrical discharge. Okay, the electro discharge machining and electro discharge drilling. With the respect of this workpiece materials, you can use a hybrid machining process. If that it should be the electrically conductive. Workpiece is electrically conductive, and electrical portions difference is built up with between the workpiece and tool materials. Okay, and the material removed by the controlled erosion through a series of electric spark between tool and workpiece. Okay, and the electrode in submerged in dielectric. You can maybe use kerosene oils or EDM oil. Um, okay, the dielectric fluid insulate the electrode from the workpiece materials until the voltage is sufficient, is ionize the fluid and create the spark path through the field. Okay, at uh, as gap between this point, the higher temperature spark eroded a small crater from the surface of the workpiece, and the current is then switches off, and the erode materials flushed away. Okay, and the working principle of behind this electro discharge drilling is similar to that the EDM machining process, existing EDM machining process. Okay, the spark is generated between the rotary tools electrode and workpiece materials. Okay, the electro discharge drilling is a potential drilling process of hole making resulting from the its characteristics are being to the conductive materials only. Okay, and hole grinding process, electro discharge hole grinding is an accurate way of the hole grinding and the surface finishing of the hole which has been the previously produced by the electro discharge drilling. Okay, in order to the improve of this surface finish of the hole to being into a accurate size, the hole is drilled slightly undersized. Okay, the tool used for the hole grinding is known as a diamond coated cylindrical tool. Okay, which has bottom and the side grinding faces. The hole grinding cannot suitably of use of this rigidity of these holes and in the conductive and the difficult to machine or advanced materials. Okay, it simplify follow the whole path which has been previously drilled by using the electro discharge drilling, and materials in removed in the small amount from the whole wall surface. Okay, this electro discharge drilling and developed electro discharge drilling and hole grinding is the combination of electro discharge machining, electro discharge drilling, and hole grinding. Okay, the motivation of the research in the area of the machining science and technology can be attributed mainly the basic point. First is the existing materials to existing machining. Okay, or existing machining to existing new materials. Okay, then second one is the new machining to existing materials, and third one is the new machining process to new materials. Okay, existing materials means aluminum, mild steel, stainless steel, inconel, and all those things. Developed materials or new materials means MMC, hybrid MMC. You can use uh, developed materials only. Okay? Okay. The advantage after this combining this electrode discharge grinding process and electrode discharge drilling process is remove or reduce forces, eliminate resolidification layer, and reduce the residual stress of the surface of the workpiece. Okay. Next slide is the overview of the literature review. The first figure shows the percentage distribution of the research studies conducted in the field of unconventional machining process or advanced machining process in the various materials. Okay, on the various materials. The largest percentage of studies concerned with the thermal process, such as electro discharge machining, electro discharge machining, and electro discharge drilling. Okay, for hole making. Okay, approximately 50%. Followed by the chemical and mechanical processes, 31 and 32. Okay, respectively. In figure number uh, 2, the figure B, it shows the emphasis of the using the unconventional machining process has been for the conventional energy materials such as steels. Okay, use a 52%, and only 9% of the study focus on the applying the concern of the conventional method of the material removal. Okay, for the advanced material or such as a MMC. Next one is the various process variant of EDM are 40%, and wire electro discharge machining use the 23%, and ultrasonic discharge machining is 21% use, and electro discharge milling 11%, and others electro discharge drilling, electro discharge grinding, electro discharge diamond grinding, electro discharge phase grinding uses only 5%. Okay. In next slide, the this slide is overview of the various type of processes variant based of the EDM units. Okay. This figure also shows the EDM processes can be subdivided according the machining of process being carried out. Okay. For example, electro discharge grinding, electro discharge phase, or electro discharge phase diamond grinding, electro discharge cutoff grinding, electro discharge dressing, electro discharge drilling, or so many units are used in this research areas. Okay. Next slide is a percentage distribution of the various electrode materials used in electrode discharge machining and electrode discharge drilling processes or micro EDM process. The major emphasis of the research work has on copper materials 43% and brass 21%, and tungsten copper used on 21%, and other composite electrode material use only 1%. Okay. The different types of tool materials has been explored for the electrode discharge drilling, micro electrode discharge machining. Okay, such as the copper, brass, copper, tungsten. Along these discharge drilling tool materials, copper tool electrode has been found be more suitable for this EDM process because of the maximum material removal rate and minimum tool wear rate. Okay, the superior performance, because of this superior performance of the copper and the brass tool electrode is highly thermal conductivity and highly abrasion resistance. Okay. A number of research articles have been focused on the area of the different types of reinforcement concentration, shape, size of the particle, properties of the particles. More than 400 to 500 research published has been publication has been published on the powder mix EDM and micro EDM units. Okay, for different materials in last decades. Next, in the next few slides, I will tell you how to develop a new materials or advanced materials such as a MMC metal matrix composite, and what challenges and problems have faced to make a specimen or a workpiece material. Okay, I will also discuss how we solve the problem using electro discharge unit of this type of EDM. Okay, such as it is called the electro discharge sewing. Okay, the first introduce the composite materials. A composite material consists of two and more than two essential parts are being to a metals. Okay, the other materials being reinforcement in the form of the particle is called the metal matrix composite, MMC. Okay, the use of MMC was over 3.5 million, okay, kg in year 2004 to 2005, and is increasing rapidly at the annual growth rate over the 6%. Okay, the most of your current applications are ground transportations in 35% approx, aircraft in 40 to 50%, in electronics area 2 to 5%, okay, and in sports 10 to 20%, and industries use a data of 2015 to 2016. Okay, there are several processing techniques available for the processing of the fabrication of a metal matrix composite. The processing and the fabrication techniques developed on the choose of the metal matrix composite, metal matrix or reinforcement. Okay, basically there are three types of types: solid phase, liquid phase, and vapor phase. For the fabrication techniques are used to producing the MMC. Okay, the commonly used these techniques include liquid metallurgy and the ester casting, also known as the compo casting, squeeze casting, or spray casting, or powder metallurgy. Okay, the MMC was developed. This setup developed by Professor Akshay Dwivedi sir in 2000 approx yearly, to not exactly remember, 2008 to 2010 maybe developed, but we are repair or me or my friend Professor Sarabjit Singh is renovate the design of these setups. Okay, the MMC ester squeeze casting process mix the reinforcement with the argon gas. Arrange a first furnace A using the melting. First furnace A is stirring, melting of the reinforcement with the argon gas arrangement, and second furnace is only used for the preheating of the particles. Okay, the melting of the aluminum Al6063 alloy and preheating the particles in furnace B is 10% silicon carbide. Okay, and in hybrid machine MMC developed by using the 5% silicon carbide, 2.5% graphite, and 2.5% aluminum oxide was carried out this in this furnace. Okay, the reinforcement particles of the silicon carbide of for MMC was preheated at 900 degrees Celsius for 3 hours to improve their wettability. The temperature controlled with the controller having a maximum range of 1200 degrees Celsius. Okay, was used. The sterile casting process was carried out around 5 to 10 minutes at a average mixing speed is 600 to 700 rpm, controlled by the auto regulator. This is auto regulator. Okay. And the semi-solid slurry was mechanically squeezed using the uh, reciprocating action, which also remove the interpreted gases or the crucibles. Uh, Metals materials was taken out from the furnace A. Okay, this is the furnace A, and then squeezed after the pouring in the rectangular mold. Okay, this is the mold, rectangular mold. This is the crucible. The metal uh, is messy state was pressurized and cleansed in the normal water. Then the distribution of the particles was uniform in the casting, and finally the composite billet or bricks was removed from the rectangular mold by unsqueezing the supporting plates. Okay. Next, the cutting action in the electro discharge sewing is employed for the imparting stationary or reciprocating motions to the cutting tools. The setup incorporate with the provision of the direction of the reversing unit or speed control to the tool, electrode, tool change, and use of the stationary tools, the current flow from the supporting attachment in this shaft casing. Okay, attachment to the discharge cutting, uh, attachment in the direction of the x direction. Okay, and this rotations is uh, drive to this blade. Okay. The aim of this phase is conceptualize or develop a cutting strategy in order to the efficiency and the effective cut of the developed of MMC. Okay, uh, into the workpiece or specimen for the testing. The developed MMC were found to be hard or difficult to cut using the standard techniques such as a hexa or power hexa. Okay. Therefore, it was the plan to develop a novel cutting techniques for cutting of this developed materials or other difficult to cut materials. Okay, the conceptualize this process lead to design and fabrications in the lab of IIT Roorkee of the electro discharge is called the electro discharge sewing process. The related aspect of this developed mechanism of the cutting are discussed in the various level. Okay, this electro discharge sewing process is one of the recent innovations for the enrichment of these capabilities of the discharge machining process. In initial studies, it has been found that the EDS electrodischarge sewing based process is very feasible and practically applicable in the field of this cutting or other applications. Okay, the since first use the hexa blade and then go to second the power hexa, then use wire electro discharge machining, and the progressive improvement have been made in this cutting techniques that could now imported to the cutting of the MMC or hybrid MMC. In this MMCs, reinforcement particles is using silicon carbide have a use which are hard and act the on the hard hand saw blades teeth is reducing their life and the cutting quality. And wire EDM is referred to the MMC cutting that form of the part of slow machining rate, wire consumptions and wire breakage problems. Okay, in an effort of to meet this cutting challenges created by this MMC process. Okay, have now we employed the include the MMC. However, this workpiece materials or specimen of this workpiece has been prepared with the EDS processes. This processes is cutting operations in which the tool electrode consists of the series of the electric spark between the blade and workpiece. Okay, the depth of cut and curve width of this EDS process usually uh, negligible or very less as compared to conventional sewing or wire electrode discharge machining. While this EDS process has wasted little tool wear and minimum machining time. Okay. In this slide, the comparison has been made between the surface quality produced by the conventional cutting and the developed EDS process. The workpiece materials is MMC was taken, which is already was half cut by the hand hexa, and this cut was a 50 length during the cutting, and this width 7 saw blades was broken. Okay, the cutting of the composite plate of 50 into 12 of the hexa processes look a 1 hour 30 minutes approximately. Okay, the whiling the cutting of this same materials length of 70 into 12 millimeter with the EDS processes look only 40 minutes approximately. Okay, the tool wear with a current level of 6 to 8 ampere was zero point 0.6 to zero point 0.2 to 4 millimeter cube per minute. Okay, and this EDS process and a unconventional cutting process un, is a very better result and feasible for this cutting abilities. Okay, it is in this figure it is clear, it is so by using this same figure is the deep scratches were present on the surface of the hexa cutting specimen, and the surface roughness was reduced significantly by this EDS process. Okay, there is no induction of any abrasive impact on this EDS process on the surface of the workpiece. Okay, next slide is the tool electrode configurations or tool geometries of electrode was machined as per design into the various profile by using lathe. Okay, this is the this studies is published in Journal of IMECI. Okay, the a comparative study of the performance of different tool electrodes of electrode discharge drilling processes of MMC is important in order to establish guidelines for the suggesting the suitability of the various electrode for the specific applications. A specific tool geometries found appropriate under the given conditions may not be equally effective under other situations. Therefore, the creation of this tool electrode or tool selections for the given set of the machining condition is essential. Okay, the material removal rate has been uh, uh, identified as the important response uh, for the various tools which has been the direct influence in the defining the productivity of this process. It has been the established earlier that the material removal rate is higher for the all rotating modes of the tool electrode than as compared to the stationary mode. Okay. In this slide, the amount of this material removal from the surface of the tool electrode and the negative polarity is so much smaller than the removal from the MMC surface is a workpiece materials or a positive polarity. The tool wear rate is an inevitable parameters to the every material removal process through not desired at all. In this figure shows the worn out the electrode after the electrode discharge drilling process. The wear was observed on the electrode face or bottom portions and at the corner of the tool after the electrode discharge machining process or drilling process. The volume of wear on the bottom and the corner portions of the solid cylindrical electrode can be mathematically calculated for the very few researcher or scientists. Okay, but there is a degree of the approximations of innovated and therefore it becomes necessary to the experimentally find out the tool wear rate during this electrode discharge drilling process. This slide shows the results of or experimented data for the material removal rate during the electrode discharge drilling process or the various tool using the various tool electrodes. Uh, the contact area between the tool electrode and workpiece is one of the most critical variables defining the performance of the electrode discharge drilling process. It has been found to be directly proportional to the spark energy. The rotation of the electrode improved the flushing and debris particle from the spark gap. This figure, the conical tool electrode lead to the maximum material removal rate. The higher contact area may lead to increase a high heat density on the surface of the workpiece within the entire electrode gap, which may lead to improvement of this material in the material removal rate. As expected, the material removal rate was found to increase with an increase in the contact area between the tool electrode and the workpiece material. Okay, the material removal rate recorded using the chamfered or the solid cylindrical tool electrode was similar. Okay, the minimum material removal rate was found with the helical tool electrode geometry. Okay, the clearly established this figure the importance of the tool point geometry as an important process parameter defining the performance of this electrode discharge drilling process. The difference of this material removal rate using the various tool geometry may be attributed to the number of the factors as a as a important factor may be the spark energy and other factor may be the degree and the types of the flushing achieved by the various geometries. The tool wear is a individual tool, the wear of the individual tool electrode and the complex interactions between the tool geometries. Okay, the dielectric fluid of the workpiece materials. Next, electrode discharge hole grinding. The grinding and the abrasive actions help to the increase the quality of the workpiece surface or surface of the hole. Electro-discharge hole grinding facilitate the machining or grinding of the whole wall using the periphery of the metal bounded diamond grinding tool electrode. The metal bounded diamond grid is used in addition to a simple electrically conductive tool used in this EDD process, electrode discharge drilling process. Tool is used for the rotating and the peripheral diamond tool electrode about the axis perpendicular to the machine table. After the grinding, the rotating tool feed toward the workpiece under the servo control of the machine, such that is the metallic bonded tools and workpiece materials are physically separated by gap. A voice located to this dielectric tank is mounted the workpiece material. Okay, then the physical contact between the metallic bond and the workpiece is avoided by the gap sensing of the servo mechanism. Okay, during the production of the surface spark between the metal bonded grinding tools or the workpiece, the abrasions of the diamond abrasive having the protections higher height or more than the inner electrode gap. However, the similarly heated the work material surface. Okay. Next slide is the whole grinding tools geometries and same morphology as presented in this figure. It can be observed from this figure that the diamond grid has irregular shape, and this figure is indicate that the diamond grid is a uniformly distribution at the periphery and the face of the hole grinding. It was found that the axis time was being consumed by using the electrode discharge drilling followed by the grinding. When with the aim of the improvement of the efficiency of this process, new tool electrode was conceptualized and developed, which was capable to discharge drilling, and this phase is capable for the discharge drilling, and this portion is the hole grinding simultaneously. The tool helped to reduce the setup times, alignment problems, and subsequently improve the surface quality. This slide shows the table summarize the optimum process parameter with the electrode discharge drilling process and electrode discharge hole grinding process based of the minimum discharge current range. Range is 1.5 ampere to 1.5 ampere to 7.5 ampere used during this experimental investigations. This figure shows the surface roughness of electrode discharge drilling is improving the produced hole at low hole surface quality. One of the key reasons in that the mechanism of the single discharge drilling are still not suitable for the hole making. The complexity of this process due to the number of electrode gap is proved to be a far sufficient discharge current and other process parameter to the hypothesize for the formation of the large debris freezing in this form of the crater. This slide shows the whole surface of drilled holes before drilling or and the after drilling that was observed using the scanning electron microscopy. The figure shows the workpiece surface of the drilled hole after the grinding. This one. The average surface roughness value is 5 micrometer has been found at the inner side of the whole wall of the workpiece material. Okay. The combination of this electrode discharge drilling and hole grinding electrode would be help of the many advantage. The combine the tool electrode would help the reduce setup times, alignment problem, and subsequently lead to the improvement of the surface quality. And second one is second advantage of this combining process is the grinding tool phase would be polishing the whole wall produced after the discharge drilling at a faster rate, which will be the improved productivity rate as well as a surface roughness of the hole. In next is fourth part is micro electrode discharge machining of biocompatible magnesium alloy. The magnesium alloy are being much popular in the biomedical industries due to their biodegradability characteristics. The biomedical implants are expected to be the desired gradually in these human bodies and promote the growth of damaged tissues. The increasing demand for the biodegradable implants required the development of the manufacturing method that can produce these type of implant in reasonable times with the better dimensions accuracy and the desired surface characteristics. The excellent mechanical properties coupled with the lightweight characteristics makes magnesium alloy and emerging energy materials for the several biomedical applications. The microelectrode discharge machining is an excellent method that can be used to make the component with a higher dimension accuracy at the micro level. In this research study, the primary focus the research to is to achieve the enhance the machinability in terms of the minimum machining times and the dimensional deviations of the magnesium materials. Okay, by using the micro EDM process. Okay, the machine surface or the tool electrode were analyzed through the FSM or EDX or XRD. In the present study, this is the figure of Hyper 15 Synergy Nano Systems machine. Okay, the investigate of the micro EDM of chosen work specimen is magnesium alloy, and the composition of the work materials is used to AZ91D. Okay, several experimental trial was done by my research scholar performed in NIT Meghalaya labs to achieve the machining depth of 1 mm and previous studies of cryogenic treated tools and cryogenic conditions using this machining process. Okay, a set of copper and brass tool electrode of 570 micrometer of the diameter was dipped in the cryocoin containing liquid nitrogen, okay, NL2 at a temperature of minus 196 degrees Celsius for deep cryogenic treatment. Another set of the copper and brass tool electrode was left untreated. Okay, the first condition is treated cryogenic treated tools, brass and copper use, and second one is the untreated copper and brass tool use. Uh, the temperature of the tool electrodes to be cryogenically treated slowly brought down to the minus 96 degrees Celsius at cooling rate is 1 degree Celsius per minute. Okay, and then brought back the room temperature at heating rate of 1 degree Celsius per minute, and the tool electrode were dipped for 24 hours in the um, liquid nitrogen environments. Okay, the figure C and D shows a set of untreated copper and brass tool electrode, and figure E shows the clamped work material machined by the untreated tool electrode using the micro EDM setup. Okay, the model of this micro EDM is Hyper 15. Okay, Synergy Nano Systems. This figure present a AutoCAD based on the AutoCAD models of the machining process of both copper and brass tool electrodes. This is the results based of the copper untreated copper tool electrodes and treated copper tool and brass tool electrodes. The copper is better conductor is of electricity, or thus the significantly reduce the machining time, and both untreated tool and cryogenic treated conditions. The cryogenic treatments enhance the properties of the tool electrode, which result in improved machining performance. The where UCTE means untreated copper tool electrode, and CTCTE means cryogenic treated copper tool electrode. UBTE means untreated brass tool electrode, and CTBTE means cryogenic treated brass tool electrode, where the machining time and cryogenic treated brass tool electrode was increased as compared to untreated brass tool electrode. This is possibly due to the substantial decreases of the electrical resistance in the cost of cryogenic treated copper tool, brass tool electrode as compared to the untreated brass tool electrode because of deep cryogenic treatment. Okay, the comprehensive review report on the many researchers considerable reductions of the residual stress which are developed during this machining process or manufacturing process as result of the cryogenic treatment. Okay, thus deep cryogenic treatment detrimentally affects of the performance of the cryogenically treated of the brass tool electrodes. Okay, the comparative uh, representation of this machining mm, electrode is cryogenic treated copper tool electrode result is latest machining time with the minimum dimension deviations. The copper has better electrical and thermal conductivities as compared to brass. Okay, this slide shows the minimum value of the average dimensions deviations machining of each tool electrode by using the optical microscopy image. was taken for the 100x magnification. Okay, the corresponding FESM image obtained at a magnification of 2500, okay, of the surface machined by the each tool electrode. In each optical microscopic image, the diameter marked by yellow color represent the diameter of hole obtained after the machining, which is more than the diameter of the tool electrode. The figure B shows the optical microscopic image and FESM image obtained by the cryogenic treated copper tool electrode, where the optical microscopic image of this machine surface present the minimum dimensional deviations from the visual inspections for the same surface appeared have to the maximized amount of the oxide formation. Further, the comparative study of the EDS analysis of the accumulate this oxidize on this different machine surface confirmed with the visual inspection finding the display of the same image. The rise of the oxide contents may be implied toward the improve the machinability and the corrosion resistance of the tool work materials, work materials. A low amount of voltage, approx 130 volt, was applied during this micro EDM machining of the chosen materials. This amount of voltage is sufficient of the formation of the oxidized by the promoting the polarization of these metals. The figure B represents the FESM image is magnification in the 5000 of the surface machined by the untreated copper tool electrode and cryogenic treated copper tool electrode, untreated brass tool electrode, and cryogenic
It's 11
treated
o'clock.
brass tool electrode. Some accumulated debris was visible on the machine surface. In figure A, shows the clear view of the thermal micro cracks and the thermal patching, which obtained by the resulting of the fragile fractures of the machine surface due to the continuous sparking to the accumulated debris. In figure B, is present of this machine surface with the latest number of the micro cracks and the maximum amount of oxide formations. The oxide and hydroxide of magnesium, zinc, copper are presented in the oxide layer. The softened structure of the oxide is spread over the machine surface and formed the layer. Okay, the oxide layer act as a positive or progressive layers on the surface of the workpiece, which prevents further the corrosions by the reducing the electrode transport of the chemically reactions with the base metals. Okay, and figure shows the machine surface with the maximum number of thermal micro cracks and micro pattings. Okay, the micro pets of this gray or frosted appearance can be seen along with the micro cracks, which is an indicator of the fragile fractures of the machine surface. Okay, these damages accurate due to the local corrosions in the regions cracks through the impurities of the debris inclusions. Okay, the figure D shows the machine surface consisting of the moderate number of micro cracks. This figure shows the depict the EDS of the surface machine by uh, untreated copper tool electrode and cryogenic uh, treated copper tool electrodes. And this figure shows the untreated brass tool electrode, and this is the EDS of the surface machine by the cryogenic treated copper tool electrode. Each EDS plots demonstrate the variation of the oxide and the carbon contents after the machining by the different tool electrode according to the obtained EDS data, which correspond this figure A, B, C and D. The percentage rise of the oxide contents was 31%, 30 second in second figure 39%, in third figure 15%, and fourth figure is 34%. The figure B, the maximum percentage rise in the oxide contents and the maximum amount of the oxide formations were noted in this case of the surface machine of the cryogenic treated copper to electrode. The However, the exact amount of oxide formations can be experimentally calculated in the in the future research or future scope of this research. Okay, the cryogenic treated copper tool electrode was found to produce a least number of microcakes on the machine surface, uh, followed by the untreated copper tool electrodes. The presence of more amount or carbides on the surface of the workpiece results in the more brittle surface. This slide shows the crystalline natures and the eliminate present of the untreated surface or surfaced machine by the uh, untreated brass tool electrode, untreated copper tool electrode, and cryogenic treated brass tool electrode and cryogenic treated copper tool electrode were assessed through the XRD analysis. This figure A, B, C, and D present the FESM displaying the recast oxide layer formed on the surface produced by the untreated and treated uh, conditions by using copper and brass materials. The thickness of each oxide layer was measured of the several uh, distant locations on the machine regions with the help of FESM thickness measuring facilities. Okay, the average thickness of this oxide layers was mm, 2.9, and in this figure 3.3 average values, and third figure is 1.8, and fourth one is 2.44 micrometer obtained by treated and untreated uh, conditions. The tool electrode is higher thermal conductivity and more refined grains can be achieved the higher uniformity, thickness and integrity of the oxide layers. This figure is present uh, the tool geometry using the figure A shows figure A to B is the equal magnifications, and while C and D is taken the different magnification. The reason of this increasing this magnification was see the one of the reasons more clearly in the case of the untreated and the treated brass tool electrode, since they was were not clearly visible to the 250 magnifications. All the microscopic image.
We left. I think some connectivity, okay, some issues are there. Okay, I think our expert is having some connectivity issues, so I need to connect him. Okay, so he might join us very soon in couple of minutes. Okay, so I'm just getting connected. Hang हो जाएगा सर. कोई बात नहीं. यहाँ से चैट दिखेगा सर, ये स्पेस कोई बात नहीं, रुक जाओ. हो जाते हैं, वो हैंग हो गया. सब हो जाता है क्या? हाँ हाँ. अच्छा, कई सारे ज्वाइन कर रहे हैं यूजर पुराना. ये पूरा चैट लोड करता है. पूरा क्यों करता है? मेरे इसमें आता नहीं सिस्टम में. एक से कोई बात नहीं. इसका वैल्यू still okay. I need to So, dear participant, I got connected to our expert. He's just joining us in couple of minutes. Okay, so please be there. कोई connectivity से related issue था शायद. So these are the some shortcomings of these online facilities. Okay, so we can't control these all because, but it provides us the facility to get connected beyond the regions, beyond the states, countries, and all. Okay, so these are the some benefits also. So okay, so let's see. Okay, so we are waiting for our expert now, so he can continue his talk.
Now it is visible, sir. Hello.
Yes, sir. Yes, sir. You are visible, sir.
Oh, sorry. Due to some network issue. Okay. Uh, okay. The powder mixed micro electro discharge. This is the powder mixed micro electro discharge machining process. This process was found to improve the quality of the biodegradable alloys and um, my research scholar was used in this experimental study to investigate the machinability of this magnesium alloy and the effect of this. These are the input control variables on the machining times and dimensions, deviations, and the characteristics of this machine surface was experimentally investigated. Okay, and the experimental investigate this effect of the zinc powder particles concentrate in this mm, perspex box and copper and brass tool used during this experimental process by using the powder mixed micro electrode discharge machining. This is the tabletop type micro machining machines. Model is Hyper 15 synergic nanosystems. Okay, the sparking phenomena of during this powder mixed micro EDM process. The existence of this powder particles between the tool workpiece electrode consequently is increase the discharge gap and reduce the spark intensity heating the work surface. However, the spark intensity varies the powder particles concentrations and the breathing effect among the conductive powder particles formed between the electrodes can be lead to the weakening of the insulating strength of the dielectric. As a result, early discharge may occur leading the short circuit. Okay, this figure shows the phenomena or sparking phenomena during the non-powder mixed, without powder mixed micro EDM and powder mixed EDM performed at different powder particles concentration. The figure A shows that the spark directly strike the work surface during the uh, uh, non-powder mix or without powder mix micro EDM. And figure B2E display the behavior of the sparking during the machining with the powder particles mixed in the dielectric at different concentration. It is clearly uh, it is clearly evident this except 4 gram per liter powder particles concentrations, all other concentration in um, of the poor machinability. At 2 gram per liter concentration, the spark lead travel via the powder particles but could not strike the machine surface with the desired intensity possibility due to the weak bridging effect between the tool and workpiece electrode. The surface was notice that the poor dimension deviations since the powder particles concentrations failed the uh, fixate the spark onto the target spot of the work surface. Okay, as a result of this formation of this more crater and heat affected zone is generally noticed. However, the 4 gram per liter powder particles concentration result is formations is slowed or is
हेलो डॉक्टर अभिषेक सर सर
58
वॉइस सर नहीं आ रही है, थोड़ा सा वॉइस का इशू है सर, प्लीज चेक करिए। हेलो, स्लाइड्स आर विजिबल बट वॉइस इज नॉट कमिंग।
58
Okay, I think some connectivity issue is there
Navina.
still. Okay, dear participants, I'm just getting
59.
connecting to our expert.
60
हेलो, यहाँ से तो आ रही सर। हेलो, अभी आ रही है? हेलो, ओके ओके ओके।
Participant, I'm just getting connected to our project expert again. Some issue still. Hello. I'm getting connected to our subject expert. Okay, so let me get connected. Maybe some connectivity issue still not of. Okay. ये बजा रही थी ना अभी. So, dear participant, our expert is now with us uh, on call, so he will respond the query. Sir, am I audible to you?
Yes, yes.
Yes, sir. Actually, one question asked by our one of the participant. He's asking that how to improve machining sharp corners on the workpiece using electro discharge machining.
Okay. Actually, first, previously I have told is we have developed in one tool is combining with the electro discharge drilling and hole grinding. First, we have used in suppose you can make the hole in the hard materials. Okay, the first drill and then go to the coated tools use. Okay, the coated tool use because of the rubbing of the wall surfaces. Okay, after the rubbing, the wall surfaces is improved and the sharp corner create with the on the workpiece surfaces. Okay,
Okay.
and thus extensively studies of this required of this powder mix EDM and electro discharge showing. Okay, only is this segment electro discharge machining segment. Okay.
Okay, sir. Thank you for your kind response.
Any query or further query?
Participant, you can write some more query if you want to ask. Okay, because most of the content already been over by Professor Abhishek, sir. You can write your queries in the chat box, or either you can raise your hands so that I can allow you to unmute.
Okay.
So just a minute, we are waiting for 1 minute more.
Okay, sir.
Maybe
No
some
problem.
more participant can ask. Okay. So dear participant, you can ask some more queries, okay, by writing in the chat box.
Hello.
Yes, sir, we are waiting just for a few more seconds.
Okay,
sir.
okay. Okay. तब तक मैं एक announcement करता हूँ. I want to make a small announcement.
Okay, sir. Okay.
That it may be beneficial for you and all the participants.
Definitely.
NIT Patna Mechanical Engineering Department is organized one international conference from 5 to 7th August 2021. Okay. This conference, international conference, all accepted papers will be published in SCI Journal or ESCI Journal, Scopus, or remaining papers will be sent to the LCVR for the book chapter. Okay, and we also organize in next week one adult course based on the novel materials. Okay, and okay, sir.
Okay, thank you so much, sir.
Any
For
query?
your no more queries there, I think, and participants are
no problem.
appreciating your
Okay, thank you, sir.
delivering.
Thank you very
talk.
much. I especially thanks to coordinator Dr. Ravi Pratap sir is calling here, and due to some technical issues and network problems. Okay, sir.
Thank you so much, sir, for your
later.
definitely, sir, and we wish you very all the best for your coming course and the coming conferences. Thanks a lot,
Okay,
sir.
thank you,
so much.
thank you.
Thank you so much.
Okay, thank you all.
Thank you. So dear participant, so the first some issues were there, but okay, at the last the queries and all the things have already been covered by our subject expert. Okay, so it was about the first session we just completed. Okay, we are just waiting for our next expert, Professor Pradeep Kumarji from IIT Roorkee. He will join us very soon so that we can start our next session. Okay, so the second session is going to be more interesting. It's the second talk from Professor Pradeep. हेलो जी सर, गुड मॉर्निंग। सर मैं अच्छा आप तो सर आपने बीच में अच्छा मैं चेक करता हूँ। हाँ सर आप ज्वाइन है सर, ज्वाइन आप ओके सॉरी सर मैं देंगे वो आपसे। So dear participant, our next session expert, Professor Pradeep Kumarji from IIT Roorkee has already joined us actually already. So I will just extend my request to Professor Pradeep Kumarji to share the talk with the participants. So you are requested, sir, please.
Ravi, can you see the presentation?
Yes, sir, it is very clear and visible.
And slides are moving also?
अभी सर इसको स्लाइड व्यू में कर लीजिए सर इसको,
स्लाइड व्यू में I had already done in slide view.
Yes, sir. Now it is in slide. Yes, sir. Sir, yes, sir. It is moving. It is moving.
Okay.
Okay. Yes, sir.
Okay. Thank you, Professor Ravi, and giving me the opportunity to talk on this joining
Yeah,
of material
my
through
pleasure.
microwave energy. Am I audible also? No?
Very clear, sir.
Okay. Thank you. So basically, this topic, I should not say now it's novel because last 8 to 10 years, a lot of research is being conducted at Roorkee, and this is initially when we started, it was like that whether we will be able to do it or we will not. So finally, we could achieve the success. Our group has filed the patents also in this area. This is basically joining of the metals in by using the microwave energy. That is the thing. So just let me start it. It's the microwave processing of materials. It is, you can consider, because it is new field and a lot of amount or considerate amount of research potential it has. It is accepted as a novel method because it offers specific advantage, mostly in terms of time and energy efficiency. So, because we tried to do the welding, many other we prepared composite, etc., drilling, etc., we have done it by using it. But the important is it is very time saving. Lot of times in suppose in welding you take 10 minutes, we here basically in 1 minute we do it. So not only the time and certainly time and energy are related with respect to the power. So it is basically it offers the specific advantage in terms of time and energy. Most of you must be having the microwave oven in your houses, and you know that we have specific materials. When we heat something in that microwave oven, we have the specific utensils that we use. Can we use the metal? The answer certainly will be no. We cannot use the metal. Why you cannot use metal? What will happen if you use the stainless steel or brass or any metal inside and heat the things that you want to heat it? So because the moment you put in, a lot of sparks started coming, and basically if you are basically heating it by keeping the material in some metal, it will spoil your microwave oven because sparking will be there, and if it is for more longer duration, the microwave oven will be gone. So that with that thing, let's see what is microwave. They are the electromagnetic waves. Everybody knows that they are the electromagnetic waves. What are the electromagnetic waves? It is an oscillating disturbance that contains energy. So electromagnetic waves are basically a oscillating disturbance containing energy. So these waves are formed when an electric field is coupled with a magnetic field, perpendicularly to each other and to the direction of wave. So they are basically coupled, electric and magnetic field are coupled, and they are at 90-degree phase difference, and they move in the direction of the wave. So that is basically the electromagnetic wave. The frequency, second important part is the frequency. That microwave lie between radio frequency and infrared frequencies. If you see the frequency spectrum, electromagnetic spectrum, so you can see here that on the left side increasing wavelength, increasing energy. And if you see the spectrum, that low frequency corresponding applications are also given at the bottom. So when this is low frequency, power lines, radio, AM, FM, then it comes microwave. Microwave frequency basically is in between radio frequency and infrared. And wherever the infrared frequency is there, we basically use in the heating, radiant heat, then visible lights come, then ultraviolet, your arc welding, X-rays, medical X-rays, gamma rays, radioactive. So this is the complete spectrum of the electromagnetic energy. And microwave specifically, because we are talking with respect to the microwave, They lie between the radio frequency and infrared frequency. Microwave frequency numerically is in the range of 0.3 gigahertz to 300 gigahertz, and wavelength is 10 mm to 300 mm. In a vacuum, electromagnetic radiation propagates at the characteristic speed of the light. Okay. So these are some information with respect to the electromagnetic wave. Then pioneers in electromagnetic wave research, some background, some history. It started way back in 1832. Then Faraday, Michael Faraday, he basically first time he observed electromagnetic phenomena with the wave motion, sound or light. So that was the first beginning when Michael Faraday, he observed this phenomena. In 1846, James Clerk Maxwell, he basically formulated mathematically the phenomena, electromagnetic phenomena with the interaction of electric and magnetic field. He simulated it. So mathematical model he developed. In 1888, the Hertz, he observed that radio waves could be bounced off objects just like sound wave. So he observed when he just used the radio waves, when they attack the metal, any metallic object, it bounces back. So that is the first observation in 1888 that he observed that radio waves are bounced off when they basically attack, when they come in contact with any metal, just like the sound waves. Then 1904, Christian Hülsmeyer patented principle of radar. Because based upon the earlier observation, he did further research and he patented the radar. What is the radar? Reflection of electromagnetic wave by metallic objects. Because to locate the ships through fog, etc. So many applications are there. So, but that was the first time he did the research and he finally patented the principle. Then Clavier, A.G. Clavier in 1931. So first time the microwave communication link between France and England, Calais in France and Dover in England. So they had developed a communication link through this electromagnetic wave. So they developed a communication link so they can basically talk and then send the message and like that. And in 1940, Harry and Rendell, first time they developed cavity magnet. Cavity magnetron is basically the source to generate the microwave energy. So they developed a unit through which you can convert the electrical energy to the microwave energy. And 1945, first time Percy Spencer, he discovers microwave. So he discovers microwave oven. And 2000 onward, so many applications are reported with respect to the use of the electromagnetic wave or by the microwave oven that was developed. Now coming, that was a part of the history, just how it started from Faraday to Spencer, and finally we could get the microwave oven, right? Because our focus is microwave. So that processing of material using microwave energy, that lot of work was being done between this, the beginning, 1978. And most of the work at that time was focusing only on the ceramic and ceramic composite material, means non-metallic. So it is being used for heating purpose, for the non-metallic purposes. Metals were earlier considered not viable to process through microwave because it reflects microwave at room temperature. So because when you keep the metal, then what happens, that sparking occurs. Not viable means heating metal in microwave leads to different results because metals are electrically conductive. Bulk metal at room temperature reflects microwave due to low penetration depth. Because when microwave attacks the metallic thing inside the oven, so that basically reflects back. It is, the energy is not being absorbed by the metal. The phenomena is that if a microwave energy can be absorbed in any material, then only it converts into the heat energy. But in case of metals, because of the low penetration depth, because this microwave energy could not penetrate the metallic object, and it basically reflects back. And as a result, what happens? Setting up a high voltage between metal and the magnetron. Magnetron is the source of energy, source of microwave energy. So microwave energy goes to the metal, reflects back, and in the process, the high voltage is being developed between these two. And when this voltage surpasses the threshold, when threshold voltage is there, the discharge starts. So it discharges as a visible spark. You can observe it, you can check it, you keep the metal and you will notice there is a lot of sparking happens in the microwave oven. So metals were not viable earlier. The reason I told you that, what was the reason? That penetration depth was small because it could not penetrate much into the metal. And that was a major hint to us when we started this work, that okay, if anyhow we can increase the penetration depth, can the metal absorb the microwave energy? Because the reason of getting the sparking was low penetration depth. And that was one question was there, can we increase that penetration depth so that microwaves are absorbed in the metal? Because once it is absorbed, then whether it is a metallic material or a non-metallic material, the behavior is the same. Recent literature indicates that it is possible to process metallic material under certain conditions. So that was also reported when we started. Some people have done sintering, brazing, joining, etc. Just one of type of application were reported elsewhere. And nowadays, microwaves are being extensively used in heating processing application. So that is the present status. Now then question comes, how the heating happens using the microwave energy. So materials can be heated. When I'm saying material, it's not always metallic material. It can be any material. So it can be heated rapidly, uniformly, selectively, and certainly less expensively. Another significant feature of microwave processing is instantaneous bulk heating of the material. The only thing is that once the microwave energy is absorbed, so that the metal or material that absorbs the microwave energy, it becomes the heat source. So once energy is absorbed, that energy converts itself to the heat energy. So this is the conventional heating system. Here some sample is there, some material is there. When you heat it, heat comes from outside and sample is heated. But in microwave energy, so once microwave energy comes, that microwave energy is being consumed or stored or absorbed by the material. Once energy is absorbed, then this energy converts itself to the heat energy. So that's why I written heat is generated internally within the material instead of originating from external source. So in the conventional, it is from the external source and transmits towards. But in this case, energy is absorbed here, then transmits outside. So this thing that you can also notice, suppose you put a gulab jamun in your microwave, you will see the core of the gulab jamun is more hotter than the rest of the things. So because energy is absorbed there, then it starts converting into the heat energy. That's why we say it is the inverse heating profile in the microwave. Just one more schematic diagram of the same concept. This is the conventional heating. Heat sources are there. In the microwave heating, basically microwave energy comes and being absorbed by this material, and then heat energy is basically, this energy basically converts itself to the heat energy. So microwaves are not the forms of heat, it is rather form of energy, that already I mentioned. So it is not any source of heat, it is a form of energy that is converted into the heat energy. Most common microwave frequency in India that is being used, because you cannot use other than the specified legal frequency. So the legal frequency for India is 2450 microhertz, And every country has the different like this. That in Great Britain, the frequency megahertz is 896, North and South America this, and other parts including India that this. Because that is a, you can say, industrial and scientific medical frequency band that is given by the government, and it is a regulatory agency. So your frequency is fixed. You cannot use, suppose you want to use 896, you cannot use in India like that. So that is a legal matter. Then how the microwave and material interacts. They interact basically, there are three possibilities when microwave energy is interacting. This is the material. So one type of material is that it is transparent. So microwave energy comes in and passes through. So that is also not of any use. Once if I keep the material and microwave energy passes through, that is a transparent phenomena. So I am not getting the benefit of the microwave energy. Another is opaque, when microwave energy comes and reflects back, like in most of the metals. So that again also it's of, we are not utilizing the benefit of microwave energy. We can only utilize the benefit of microwave energy when microwave energy is absorbed. So there are three possibilities are there, and that is the best application is possible only here, that when microwave energy is absorbed in the material, whatever the material you are using. In metal, as I already mentioned, it reflects back. The reason I told you that penetration depth is very low. Okay. Then I already mentioned the microwaves interact with materials selectively, sometimes transparent, sometimes absorbing, sometimes opaque. Microwave material interaction depends upon the electric property. So one clue was there, low penetration depth. Second answer, we got it, that the interaction between microwave and the material, any material, that depends upon the dielectric property. So then again question, clue was there, can we change the dielectric property of the material? Then it says higher the dielectric loss factor, higher is the interaction. So that was the another answer, possible answer with respect to the microwave energy and metal interaction. That this already I mentioned, the heating of the solid material takes place by energy conversion, means microwave energy is converted to the heat energy. The material as a whole, already I mentioned, absorbs microwave radiation and converts into the heat, already told you. Only material that absorbs microwaves are heated, already I mentioned, and the material itself becomes the heat source. I already mentioned this. Then this is the mathematical phenomena, already well established, that energy absorbed by the material is given by this formula. And if you see this formula, that frequency you can't change, frequency. Magnitude of electric field, it is also constant depending upon the type of microwave you are using. That basically dielectric loss factor that I mentioned in the previous slide, that is a material dependent. If dielectric loss factor is higher, so chances of absorption is more. So that is one of the factor that this dielectric loss factor is material dependent. So when it is a material dependent, you cannot change it, because every material has its own dielectric loss factor. So that clue that we got it, that if we can change the dielectric loss factor, we can make that material more absorbing. No, because every material has its own dielectric loss factor. Then coming to the hybrid heating, why we are saying hybrid heating? I will explain just now. This is the formula, that is delta skin depth. Because I mentioned that in metals, microwave energy, the penetration depth is very low. And when penetration depth is low, that's the reason microwave energies are not getting absorbed. So that penetration depth, that normally we say skin depth, depends on these factors. And if you see this factor, that is rho is the resistivity of the material. This is the frequency of the thing, you can't change. That is a magnetic permeability. That basically is the point here, that is absolute permeability and relative permeability. So why we are saying hybrid heating, I mentioned here. There are two types of heating. One is direct heating, one is the hybrid heating. So direct heating is any material that absorbs the energy. For ceramic, say for example, and non-conductive material which are good absorber of microwave. So you need not to do any modification in that. You keep the ceramic, it will be heated inside it. That is a direct heating. When I say hybrid heating, for metal which are mostly reflector of microwave, but becomes absorber of microwave once threshold temperature is reached. Means it says hybrid heating is possible when your metal is at some higher temperature. It's a preheating type of situation, that if you keep a preheated metal in the microwave, the energy absorbed will be higher than the metal which is not preheated. Now the question comes, because that is a good clue that hybrid heating is possible once the metal is at higher temperature, and the higher temperature basically will increase the skin depth, So with that understanding, we thought let's have an hybrid heating in the material, because one option is heat the metal outside, preheat it and put in the microwave. That did not work. So we wanted an option that before actually melting or heating the metal, we should develop a system so that preheating is also there, because once the preheating is there, the skin depth will increase. So this is the arrangement, first arrangement we had made like that. If you see this, that black part is the turntable in the microwave. You have seen some circular or rectangular turntables are there. And if you see the arrangement here, that this is the base metal. These two are the 5 is the base metal, the cross hatching lines. If you see, 2 metallic pieces are there, and there is a gap. This is a butt joint we try to, and in the gap basically we put the powder, metallic powder. Same material, same metallic powder, we put it here. And now we wanted to heat only this portion, just metallic powder portion, and little bit here, right? So rest of the portion we don't want to heat. So what we did, we kept, if you see this black plates are there, that basically is a masking material. And this masking material that we kept, so that this masking material is a basically they do not absorb the microwave energy. Means insulating material, you can say that it works like an insulation, so that this much portion is not heated, only the heated portion is here. In this portion basically, if you see the center portion, we say as suscepting material. Suscepting material is they absorb the energy, microwave energy, and converts to the heat energy. Our objective was that when the microwave energy is coming on this above plate, so only this much portion absorbs the energy, and once they absorb the energy, heat is converted. So this much portion that we want, the powder portion and little bit on the either side, this much portion is heated. So that's the arrangement we did. And we got success in that, because of this, some heating is there on all the parts. And because of the heating, what happens? The penetration depth, that is the skin depth, is increasing. The more the skin depth, more the absorber. Okay, I will show you the mechanism also. So this was the arrangement that we did in the setup, and we basically got success in doing that. This is basically the mechanism of joining. So this basically, if you see that this diagram, so microwaves are coming incident and there is a reflection, because metals normally do not absorb it. And the reason is because of the low penetration depth, that is delta 1, skin depth. So at room temperature, so microwave energy coming and going up. So when temperature is at room temperature, this is the phenomena. So we say it is a negligible microwave absorption. On the second part, if you see here, that if you at the local T temperature is at elevated temperature. What is elevated temperature? It is greater than the room temperature, certainly less than the melting point. So we heat it by using the suscepting material, the portion, that specific portion that we want to heat it, we heat at elevated temperature, but certainly less than the melting temperature. The benefit of heating is that the skin depth increases. So when the skin depth increases, delta 2 is greater than delta 1. So some of the energy is absorbed, some of the energy is reflected. So partial absorption of the microwave energy is there, and some of the energy is basically reflected. So this is how basically we heat the metal in the microwave. And so these are the particles. Metallic powders are there. Metallic powders are there. So when this happens, when the heating happens, skin depth increases. So these particles starts basically fusing, and these particles gets fused together. This particle gets fused. You can see here, powder particles bonded there, because if fusion happens at the border of the main plates and with the powder and among themselves also. So particles melted and fused together. That is how basically the mechanism of joining in the microwave oven happens. So a lot of benefits are there, but two benefits I told you: time, energy, and all this. This is efficient. Cost saving, time and energy, reduce floor space, rapid heating of thermal insulators, precise and controlled heating is also possible. Selective heating, remember we only heated the center portion, so selective heating is also possible. Volumetric and uniform heating, because your metal or material absorbs the energy, so that's why it's the uniform heating is there. So heating is not coming from outside, heating is being generated from within the material. Reduction of hazardous emissions, energy efficient, environment efficient, environment friendly, clean and quiet. So these are the benefit of processing by using the microwave energy. So that was basically the development stages that happened. Then we actually did some experiment. So if you see that this was the microwave oven, very conventional oven we have used. So make was LG, and frequency I already mentioned. Frequency is fixed, exposure time varying, and power is 900. Means we can only, in the beginning we can only vary the exposure time, but later we have taken lot of permission. We did some project for the BARC, Bhabha Atomic Research Center, and we did a lot of research on that, but we were having the limitation of fixed frequency. Then we took permission from the government. It took almost a year to take permission, and we have developed a bigger microwave. There we can have all the parameters varying frequency, because we have certified that we will only use for the research purpose, not for any communication or any other purpose. So we got the bigger microwave where we can change the other parameters also. But for the standard available, we started with the standard available microwaves. So the first work basically that was reported by us, that we did basically joining of copper. So commercial grade copper was there. Interfacing material was the same metal, copper powder. Exposure time we kept 210 to 300 seconds. Powder size we also varied, and rest of the things are fixed. That is by the applicator. The applicator is the LG make. So that was basically the result. That if you see that these are the rectangular specimens we welded through microwave energy. Very clean welding if you see here. And small pieces also we welded. If you see these two circular pieces, and we basically got very fine joint by using it. So that was the application we did it. Then basically we also, because once we have the welded, then a lot of other properties we need to do. That okay, we should check the strength, microwave structure, and so many properties just to validate whether if it can join, whether that join can be used for real applications or not. So we basically went for the microstructure, and if you see here, so we got indentations also, that weld joint is there, bulk material is there, the type of bead basically we obtained. So this was the structure of the material after joining. We measured the hardness also, all properties we measured. So we measured the hardness also, porosity also. And basically, if you see this diagram, joint region, joint interface and base metal. So you can see that the red one is the joint interface. So the variation, although the variation in the hardness was there, but because of porosity and because of indentation, so the porosity was 1.92%. Porosity was 92%. Then the flexural property also we measured, and we compared all these properties, hardness, etc., all porosity, etc., we compared with the TIG welding. Okay, so with the TIG joints, if you notice that flexural properties, there was no, you can say, no visible cracks there, but there was a crack in the TIG. So my purpose of here telling is not that microwave joining is better than TIG. No, every process has its own process capability. Every process has its own advantage, disadvantage, etc. But only thing, our purpose was whether it is a comparable. Yes, we can do it. Fine, you can do it. But whether it can have real some industry applications. Yes, it can have. So purpose was not saying that TIG is good or TIG is bad. No, we just compared it. So for flexural properties, if you notice, we got the crack, but in TIG case, in microwave joint cases, we did not get any crack in that. Other properties also we compared. BM means bulk material, original material, and this is microwave joint, this is TIG joint. So ultimate tensile strength is 164. You can, although number appears more, but okay, it's similar. That similar UTS is obtained because that difference was not significant difference. Percentage elongation was higher. That is another, depending on what type of application you are using. So that is a good thing. And an important property for copper and copper joint, that was the bending strength was much higher than the TIG joint. So these are the observations that we put in. Then first we did same metal to metal. Then we had stainless steel. We used the SS316 steel. Same microwave oven, only interfacing material was nickel based. Susceptor material was the charcoal material, and these are the exposure time, power, etc. that we have used it. So these are the composition of the material, SS316. This is the photograph of the actually joined pieces of the stainless steel that we got through the microwave. All these properties, porosity was less, 0.78%, and again we compared with the TIG. So bending strength, if you notice, was less in case of steel in comparison to the TIG welding. So I'm not concluding microwave welding is better than TIG welding. No, I'm not. Again, I'm mentioning because many participants, many students get confused. Our only job is one thing, whether feasibility is there. Yes, it is feasible. Whether the welded joint that we obtained can be used for real application. Yes. So it depends where you want to use it. So that was the another thing. Then we also had another, means dissimilar material, means copper and steel we welded. So that is very good, that when you are having a dissimilar material, joining of dissimilar material is easy in case of the microwave than in comparison to the other welding processes. Then third part is we try to join the pipes. So this project basically we thought for industry, for some gas and you can say crude oil agencies, because gas is being transported in the pipes, and when the gas is being transported through the pipes to different countries, somewhere some crack is there. So important is how to, because when crack is there, so leakage of the gas is there. So can we do the joining right at the spot by using microwave? So that we tried it. So mild steel pipe we used it, and this basically, if you see here, two type of microwave basically used. One was having 900 wattage, another the 1400 wattage. Frequency we cannot change. Now we can change, but at that time we can't. So susceptor material basically we used silicon carbide, graphite plate, charcoal, because susceptor material is what that basically absorbs the energy and passes to that. Okay. So all these things were there, and this was the arrangement we did. This is oven, microwave oven. If you see this there, this charcoal is a susceptor material. Means basically the purpose of charcoal powder is to preheat it, because first the energy is being absorbed in the metal charcoal, and then it transfers to the metal. So preheating basically is possible here. Then we use the masking material. Masking, the role of masking material I already told you, they work like an insulators. This was the basically phenomena here. So the pipe was there, and if you notice here, high heating and moderate heating basically is there. So the mechanism of joining I already had explained to you people, and this is the result. This is the result that you can see at different combinations. We got the different results. Some pictures of the pipe joints that we did it. Because the only problem with the pipe joint is that the thickness of the pipe is very less. So when the thickness is less, by the time it joins, it melts away. So that basically we need to be very precise control of the duration of energy and the extent of energy and the power. So many factors need to be controlled. Okay. See here. See here. So this is the exposure time that we have. 360. Correct? Centering happened, joining doesn't happen. 422nd, 480. If you keep on increasing the time, you see before it joins, it melts away. The pipe itself melted away. So that was the outcome, that overheated or resolidified things happened. So that is not. So it seems the temperature, the exposure time should be somewhere in between 400 to 480 seconds for that particular size of the metal. We have done lot of work here also, copper to copper, stainless steel and stainless steel. I told you the dissimilar material, HMSEA, even the hard material, then drilling also we have done it, glass like that. So many things we have done it. So that is all about this, because it was a new topic. I did not, because many of the things have been patented. So I have not given the details of the things that we have patented. So there is a lot of time. We can discuss something else if you want, or you can raise a lot of questions also. I am here to answer it.
Okay, so thank you so much, sir, for this nice discussion with our participant. I hope that they will get benefited by your discussion, by your talk. Sir, one of the query asked by one of the participant, he's asking that any effective method of using microwave joining without using susceptible material at the joining interface.
See, preheating is required. If you are using other than the metal, then use of susceptible material is not there. But the purpose of using susceptible material is for the preheating. So why preheating is required? I told you, to increase the penetration depth. Because if the penetration depth is not increased, microwave energy will not be absorbed. So once microwave energy is not absorbed, the heating, because anything that you do with the heat, it needs heating. So that is, without that metallic system,
Professor. Okay, I think he has already joined us. So we'll listen. Professor Mamila Ravisankarji from yes. Yeah, so very good afternoon, all. Our next session expert, Professor M. Ravi Sankarji from IIT Tirupati, has already joined us. So we welcome you, sir.
Thank you. I'm there already.
Yeah. Thank you, sir, for being here. So before requesting Professor M. Ravi Sankarji for delivering his talk, I would like to share some brief about him with our participants. Professor Ravi Shankar works in the domain of sustainable manufacturing, precision 3D printing, micro nano manufacturing, hybrid manufacturing, tribology and rheology, etc. His lab also involves in the development of lab scale innovations to commercially manufacturing products, means the paper to product technology. He has published more than 60 articles in internationally and national repute journals and 80 international conferences. He has also having 6 patents in his account. He is the editor of 2 books. He has published 10 book chapters so far. Presently, his lab possesses with various funding from the BARC Department of Science and Technology, DRDL, BIAC, SERB, Science Engineering Research Board, SERB, IIT Guwahati, IIT Tirupati, and so on. So the sum of about 30 million rupees as a principal investigator is already resourced out. He has guided 5 PhD students already, and there are 8 PhD students doing research under his supervision. He has supervised 20 MTech projects and 25 BTech projects. He is also the very active reviewer and editors of various international journals from the various reputed publishers like Elsevier, ACS, Springer, Wiley, InterScience, SAGE, etc. And there are so many more to share about Professor M. Ravi, but because of the time constraint, I would like to request Professor Ravi Sankarji to share his view.
Hello?
Sir, yes, now it's hand over to you, sir.
Yes. I was connecting my earphones.
Okay, sir. So now, sir, participants are ready, so you can start.
Yeah, thank you. You are telling some time constraint. At the time I was
Okay, actually, nothing was like that. Actually, I was just briefing about you with the participant. So I was just saying that there is a lot of things to just share about you, about your research, about your publications and all. So because of the time constraint, I'm not just including these all in my briefing, actually, sir. So I'm just requesting you to share your research perspective. Yes, sir. Now it's hand over to you, sir. Please, you can share.
Thank
Yes.
you, Ravi. Can you able to see my screen?
It is completely visible, sir. It is very clear and completely visible.
Okay. Now in the full screen mode?
Definitely, sir.
Oh, thank you.
Welcome.
So I'm audible because I connected to headphones because others should not disturb. Yeah.
Yeah, definitely, sir. It is your voice is very clear, sir.
Yeah. So thank you, Ravi Pratap and other colleagues of the institute. I am talking about the area where I work very less. This is one of the area where I have only one publication or one conference and one publication. So normally I work in abrasive flow finishing. I I worked with Professor V.K. Jain in this area about one publication and one journal, which is again a prominent area in terms of surface finishing and other things. So most of the experts in this area is Professor V.K. Jain, because I am very thankful to him for sharing some of his slides for this particular presentation. So most of the acknowledgement goes to Professor V.K. Jain, then Dr. Ajay Sitpara, Manas Das, Professor Sunil Jha. So these are the people who work into the magnet, and these are our seniors in the lab, basically. I mean to say they are colleagues, some are seniors. Apart from it, many people work in the India, like Professor Pulak Mohan Pandey sir also work. I think many other people also work. So what I mean to say is that this is one of the area, but it has its own advantages and disadvantages. So if you want the disadvantages, you can ask me questions. Normally in the presentations, normally we don't keep. Okay. So the advantages and positive sides only we are going to look at. I am going to talk about a brief on the magnetic assisted finishing process, various variants, how these variants are going to help in finishing and other things. Coming to IIT Tirupati, just I would like to give emphasis, because you people are far away, because you are in the north, we are in the south. So IIT Tirupati comes in this region. Geographically, it is around 140 kilometers away from Chennai. So it comes towards north from Chennai. So we are the third generation IITs along with IIT Palakkad, Goa, Dharwad, Bhilai and Jammu. So we are doing fairly good, and we are progressing very fast as per the MHRD is concerned, because we have 90 faculties and we have more than 70 sponsored projects. So that shows that we are on par with first generation IITs in terms of getting the projects. We are, if you take the ratio of faculty to the sponsored projects, at this particular moment of time, I guess we are in the maybe a number one position, or I don't know, because that may be because of we have less number of faculty or something. Okay, so we can equally say that we are equally competent. And why I am saying equally competent is towards the next slide. So why we are equally competent? Because you can consider IIT Tirupati for your masters and PhD programs. We have a sophisticated facilities. And why you have to opt IIT Tirupati compared to other IITs? The first and foremost thing is that we have the latest equipments. If you take in terms of any characterization, if you take in terms of any specialized equipment, for example, laser assisted machining, so laser micro femtoseconds, so abrasive flow finishing, we don't have magnetic. And if some faculty joins in the area, that may be a different story. We have MEMS, we have coating technologies, PVD coatings, CVD coating technologies, tribological aspects. So for example, we are getting a universal tribometer, so which worth about more than ₹1 crore. Okay, so rheometers with tribo attachments and MRD cells. And what I mean to say is that we have the latest sophisticated equipments, and we are getting another one called CIF, Central Instrument Facility, where it is about, I don't know exact the amount, but it crosses normally more than 40 crores of equipment. Now, looking at these facilities and other things, we have abundant amount of applications, and we are going to shortlist only few students. So you should be competent enough to come and join us at IIT Tirupati. Okay. So regarding IIT Tirupati is concerned, you have two options mostly. Just I will come from the 2014, it is government announced. 2015 onwards, 2 IITs are started in the third generation out of 6. One is Palakkad, another one is IIT Tirupati. So they started operating from 2015. Rest all like Goa, Bhilai, Jammu, maybe I don't know exactly. They might have started in 2016 or something. So we have two options for masters. Most of the IITs don't have this MS program, so it is a mini type of PhD where you have to spend around 2.5 years to 3 years, depend on your caliber and other things. Okay, so looking at other things like PhD and MTech, I don't require to explain about all these things. So in MS only slightly different. What you have to do is either you have to do 1 year coursework or 1.5 year coursework, so that you can spend rest of another 1.5 year on your thesis. So it's more oriented towards your research program. So that is one of the option. Okay, so we have currently 5 engineering divisions, out of which the newly added is chemical engineering. Civil, electrical, computer science and mechanical are the old ones. We have 4 as usual, that chemistry, maths, physics, humanities and social sciences. We have some things on place and some things are started already. For example, Department of Material Science and Engineering, we are going to get soon. School of Design, same. So we are going to start either, because of this pandemic, it is slightly delayed. Otherwise, this 1 and 2 would have been on the highest priority list. So we would have started. Center for Precision Agriculture and Food Processing, it is started already, and only inauguration has to be done. So virtually or practically, what I mean to speak is that we have already started this working on that, and on this February 20th, we have, I think, inauguration of some incubation centers in precision agriculture and food processing. Why we have to concentrate on this is because IIT Tirupati located in the region of Rayalaseema region, which is a drought region of Andhra Pradesh, where water scarcity is abundant. So you have to use water precisely. So for the agriculture applications and other things, that's why we have to concentrate on precision agriculture and food processing, because if you take some of the fruits like banana, papaya, mango, and another one fruit is there. I don't remember. We have an abundant amount of fruits. For example, if you take mangoes, it will cost you like 20 to 25 rupees or 30 rupees kg. Or if you go for a basket, you may get for 150 rupees. So very abundant availability of fruits and other things are there. So if you see a country like Israel or something, they are circulating or they are distributing the fruits and other things or fruit derivatives across the globe with the geography which they have is very small. So that means that efficiently they are using their agriculture as well as food. So if we can also do that, that was our motive. So that is the one center. The 4th TIH, that is on Technology Incubation Hub, where we got we applied for 120 crores. So hopefully we are expecting another 120 crores. Initial investment of 8 crores has been arrived already. So it is on precision technologies and positioning, where I am heading one of the division called division. In their language of TIH, we call it as a vertical, one of the vertical that is called precision manufacturing, which includes lasers, basically lasers, micro machining, ultra finishing of lenses for positioning applications like GPS and other things. And 4th and 5th go in hand for me, especially for my particular lab. So 5th is CAMOST, Center for Atomic Molecular Optical Sciences and Technologies, where my role is lasers and optical metrology. These are the 2 areas that I am concentrating on the center. I am the core member of the CAMOST. I am also core member of the TIH. So, and Center for Precision Agriculture and Processing also. This is about the additional information that, and we are having a lot of positions regarding the PhD and other things. Around 60 to 70 PhDs are expected in Center for Precision Technologies and Positioning, CAMOST, and Center for Precision Agriculture and Food Processing in this upcoming year and other things. Regarding my research, basically I work into the machining, micro machining and nano finishing. I'm not going to talk much because this is not my first talk in NIT Jalandhar. So people are know already sustainable manufacturing, additive manufacturing, smart manufacturing, and bio-nanomaterials manufacturing. These are the 5 areas. Currently, we have done some work. Okay, some of the areas are there which we have just started, which where we can say that we are not the masters in that one. Including some of the areas we are not masters, we take some of the help. For example, smart manufacturing, we take support from our electrical engineering because they have smart group. So where you can convert interfacing and HMI division, where we have some knowledge on HMI, that is human machine interface and other things. How to connect the system to the hardware and electronics, whether you want to control by PLC, whether you want to control by microcontrollers, or these are type of things we are working on smart manufacturing and sensor fusion and other things. In additive manufacturing, as you know, we also work, but we also work in different arena. That is not part of this particular talk. Just I will give you a glimpse what we do in additive manufacturing in a one slide. Okay, so sustainable manufacturing. Many people know that the sustainable manufacturing is one of the most important nowadays. They are picking up. However, this particular work we have started in 2003 when I was doing my master's program under Professor S.K. Chaudhary sir at IIT Kanpur. Okay, so we work on to the development of new cutting fluid, development of new cutting fluid application techniques and other things. At that time, it was quite recent area. So we started using MQL system. We developed MQL system and the economic MQL systems and other things. Now all are outdated. So most of the things that currently we work is chemistry part. How to do the functionalization, how to make a efficient cutting fluid, because a efficient cutting fluid manufacturing is itself is a very big art. That's why always we used to have 1 or 2 PhD students. Currently, one of the PhD student who did his masters from ISC Bangalore is working with us on development of advanced cutting fluids and other things. Okay, so why we want to do this type of advanced cutting fluids is normal mineral oil based cutting fluids are a bit dangerous from the point of system and surroundings. So system stands for the operator and surrounding operators, and surrounding stands for whenever it comes to the into the atmospheric conditions, it will be expected to touch the nearby villages and other things. That is one of the basic problem. And even recently, if you have heard about the news in Yelur district, Yelur is not a district, so East Godavari and West Godavari districts of Andhra Pradesh. So there was a dumping of some this type of chemicals into the river, which causes central nervous system problems. So people are like vibrating themselves. So I don't know whether if you have seen Andhra Pradesh. So what is the problem? Main problem is that contamination of the water. So these industries, whenever they use this cutting fluid, lubricants and other things, what they will do is they try to dump into the water body. So whenever the people surrounding by, even though you are using AquaGuard or Kent or whatever they may, it cannot filter some of the things. It may be filtering many things, but some things will be still retained, which can go and act on various parts of your body. So that contamination, if you don't take it as a serious issue, the world may be at most risk. That's why sustainability plays a major role as per the today is concerned. For example, there is a conference by CARP in April, I think in Jaipur. Professor Sangwan from BITS Pilani is organizing. So you can see that if CARP type of body is organizing a sustainable conference, that means one should, as a manufacturing engineer, one should always think about its importance and other things. We also work into another sustainable aspects that is called biomicromachining. So we are started working. We have started working about 2013 on this work, and we are still continuing. But as I said, no, wherever there is a bioorganism, wherever there is a bioorganisms, the biggest problem is getting publications will be time delay, because organisms grow, they don't grow as per you. Okay, there is not a broiler chicken or something where you can give injection or something. Okay, so the biggest problem is that you have to take care about the growth. You should know the life cycle of this particular thing and other things. What we do here, it looks very simple, but it is very complicated. First, we get acidothioBacillus peroxidans from a reliable source. Then we try to culture it in a plate, whatever you can see. Culture it, then whatever the surface that you want to generate. For example, in this case, let me take the pen. In this case, assume that I want to make a micro nozzle on a copper plate or micro mixture on a copper plate. Why we have choose copper? I will come to that point. So we want to make a feature. So what you have to do is you have to do the photolithography, and then you have to expose this area. So whenever you want to expose this area, then it will be copper is exposed here, and this is the coating surface. Now you have to keep into the cultured medium. Plate cultured medium is there, and you have to put inside so that micromachining takes place. Now the question is how precisely it can cut. You can see here how precisely it can cut. This also can be generated by lasers, ultra fast lasers or femtosecond lasers and other lasers. But problem is heat affected zone will be still there for biomedical applications and other things. That's why, and this particular copper is a reflective material. So losses of lasers will be a big problem. And second problem is this is soft material. So you don't get very thin microstructures. You may get high depth because laser you cannot go below certain power. For example, if you have a 100-watt fiber laser or 2 kilowatt continuous laser like CO2 laser or something, what you can do is you cannot go beyond certain value, because, and this is soft material, so there may be a, instead of channel making, you may cut the surface itself. That's the basic problem. And you can see how beautifully the surfaces are manufactured. Now the question, as I was asking you, that why we are opting the copper. So the copper we are opting because if you see the last part of the slide, sorry, if you see the last part of this one, just where I just take a pen and explain you. This is acidothioBacillus peroxidans, what you can see here. So if you see here, once you remove acidothioBacillus peroxidans in a machining process, you will have two things. One is machined component, another one you will also get a waste thing that is called chips. Okay. These chips are normally, you can say that it is not useful for you. However, you can recycle it. Many people are using in a many efficient way. So what we are generating here is copper nanoparticles. Copper nanoparticles are much better for antimicrobial applications. That means my application is to generate a microchannels or micromixtures, for example, micromixtures and other things, and where my byproduct is a copper nanoparticles. In the market, since you are using bioorganisms, the purity will be at the best. So if you take a copper nanoparticles in the market, it will be very expensive. And the jury at IIT Madras, when we presented this particular work in 2017, we are adjudged as the best paper for the first position. So we are the guys who got this best paper award at IIT Madras in 2017. And this is a sustainability where you don't have any waste. However, I can say that there is a cell culture medium which you need to dump. And this is isotope bacillus peroxidans where, and you have mostly into the culture medium where water plus minerals are there. Even though you dump into the land, it won't cause any problem. So these type of solutions are much required because you don't have or near to zero waste. So you are getting a nearly zero waste in terms of product, byproduct, and using the chemicals. So now we also getting one process at this point of time I cannot disclose. So we are working on to the sustainable aspects of various advanced manufacturing process, for example, abrasive flow finishing process. So we are working on sustainable aspects of that. We are working on sustainable aspects of many things. So on this, I cannot say because we are still, I said no, we are still in the early stages of to comment about that, whether we really achieve the goal or not in terms of various advanced manufacturing, additive manufacturing and other things. So additive manufacturing, so we and our collaborators, currently we have already worked on bio-nano coatings and other things. Now we are increasing, we have polymer, metal and various other materials also we are going to get. We are developing bimetallic products. As you can see here, bimetallic products. These type of bimetallic products are new alloys we are developing, and we are understanding along with our collaborators what is the machining aspects of bimetallic materials. Okay, and these bimetallic materials, mostly the biggest challenge comes at the interfaces. So how these interfaces behaves with respect to tool wear, blah blah, so forces, temperature and other things. As I said, bioceramic, I think I have already presented to NIT Jalandhar about bioceramic. This particular work we have started in 2013 with a student called Rashmi Ranjan Behr. So where laser, you can see laser along with the powder pre-placement of powder, then you vary various laser input parameters to understand surface morphology as well as surface metallurgy. You can see the surface metallurgy elemental mapping, and if your process parameters will give you various microstructures like needle type of microstructures, and you will get regular porous structure and normal surfaces and other things. Why you require porous structures is that you need to do scaffolding structures. These scaffolding structures for cell culture applications and other things. So what is the basic thing that we want to understand here is that we have done on titanium. So there was some drawbacks from the tribological point of view and other things, for which to overcome that, we have to generate the super hydrophilic surfaces, and for which we have done laser texturing, and we make sure that we have titanium oxide, then functionally graded coatings we have done, and later we have understood clearly that functionally graded coatings are working fine from the mechanical point of view. Later we move towards the biological characterization. Biological characterization, first and foremost thing that you normally get is SBF studies in vitro conditions, simulated body fluid and other things. You can see here how this is our coated surface. Whatever the black surface that you are showing, it is not a black, both are white only, but apatite layer is much brighter than this. That's why you are seeing the background. This is coated surface, and this is your apatite layer surfaces. Okay, so that means that my particle material is biologically compatible. Okay, that means what is apatite layer consists of? Apatite consists of calcium and phosphate. That means that it is good for your dental as well, because we are choosing our SBF pertaining to the bone applications or dental applications. Okay, calcium and phosphate based. Now, once you see all this apatite layer formation, that means that my surface is actively interacting with respect to the body fluids. That means some body fluids are flowing inside the body that is interacting and exchanging the proteins and minerals, because of which this apatite layer, which is partially a mineral oriented layer, is forming on the surface. That means that my surface is biocompatible. You can use inside the body, but however you cannot directly go from here. You need further studies, for which you need to study for orthopedic applications. People normally study various osteoblast cells. Okay, so in the present case, what we have used is MZ63 osteoblast cells, and one has to understand in the fluorescence microscopy. The fluorescence microscopy give you multiple details. For example, from all these 6 images, what you can clearly see is that whether the cell growth is happening or not, that you can check. Second thing is that any foreign body or growths are there, that you can also check. The third and most important is what is the cell density, how many cells are growing per unit area, for which you should know what is actin filament, as well as what you should know what is the nucleus. So for which actin filament is a green one that you are seeing in all the images. We have given 2 types of colors, one is green, another one is red. So nucleus will occupy the red color. That's why superimposing of red color with respect to green color, that's why you are seeing orange color and other things. So what you are going to measure is cell density. That can be possible only by number of nucleuses per unit area. That gives us number of cells. So you are measuring 3 things. One is how whether the cell is growing or not. Second is any foreign growths are there. If foreign growths are there, we have another one characterization equipment where we can make nanoparticles, gold nanoparticles, silver nanoparticles, and other things. We have a commercial machines to develop this from the substrate that we are going to infeed. Okay, so you can get these particles. If there is a antimicrobial effect is required, normally you can go for copper nanoparticle that we have generated from biomicromachinery application. Okay, the cell density, the third one that you can measure. So we have the basic knowledge on cell culture, we have the basic knowledge on many things. So when we also work into the biocomposites, or you can say biodegradable composites inside the body, we have developed polylactic acid from 2 means. One is lactic acid monomers, one route. Second is purifying the commercially available PLA by removing metal oxides and other things. These are the 2 common areas. Being a mechanical engineer, normally we try to prefer the second one, that is purification of commercially available PLA to make it as a biodegradable, because you can dictate what is the degradation strength that you want and what is the degradation time of those things. Okay, so once you make all these things, hydroxyapatite particles and other things, you can make bio-nanoglass, bioactive glasses and things. We have in this particular patent technology, what we have done is we have done the optimized compositions where PLA and hydroxyapatite is 2 major ingredients. Apart from it, you also have lot of ingredients. So we made fabricated Steinmann pins, plates, staples, cancellous screws, cortical screws, and other things. And the most important about this one is you don't require secondary operation. That means that this will degrade inside the body. As you have seen the previous slides, we have the knowledge on cell culture, we have knowledge on polymers, we have knowledge on hydrogels and other things. That's why we now are moving towards another area called 3D bioprinting. This is about the brief overview. We are not going to explain. I'm not going to touch much deeply. Apart from it, we have also worked in some of the defense applications and other things also. So we are going to show you, or I'm just going to brief you on various magnetic field assisted finishing processes, how you can see the traditional nano finishing process and advanced. So I'm not going to talk about traditional. I'm going to talk about advanced. In the advanced, we have technologies. However, the first one is not a part of this one. Since there is a concept called MRAFF, the fourth one that you are seeing here. This MRAFF is the combination of MRF plus AFF. That's why we just give you a glimpse of abrasive flow finishing process and other things. I don't know, some animations. Okay, so we are going to talk about this type of things. The first and foremost thing that normally we start is magnetic abrasive finishing. Magnetic abrasive finishing. This is a setup normally developed, designed and fabricated at IIT Kanpur by Professor V.K. Jain sir and his group. So many people worked on this one. As per my understanding during my tenure, Professor D.K. Singh from HMSEA, now I think it became a university, Madan Mohan Malavia, Gorakhpur. So I saw him working on this one tirelessly, and Prabhat Ranjan from Baba Atomic Research Center, and a few more students, like exactly I don't remember the names, but since I stayed a decade at IIT Kanpur for my master's and PhD, many people are coming and going. I think Vinod Khandelwal is another student who was worked on other things. So what I mean to say is that it is a simple setup. MAF, presently when I saw, recently I saw some people working on MAF. MAF is very easy to develop. You don't require much things. Only you require is either milling machine or a drilling machine. On top of it, you can develop. You can get this one. This is variable frequency drive. If at all you are looking for a variable speeds, this is Siemens variable frequency drive, and you can connect your motor and other things. You can do it. It's as simple as that. Okay. So आप कबाड़ी में जाके कोई machine tool कर सकते हैं. So you can do this one, and you can have the feed and other things are there from these drives, whatever the drives you have. So you can have a workpiece here, and you can. So only thing that you may require if you are not from magnetic field applications is that you should know about CIP particles and what is the composition. That composition is not also very complicated or something. Like abrasive flow finishing, it is a bit complicated. Here it is not that much complicated, and that's why I recently saw one student at NIT Andhra Pradesh was NIT Warangal. So NIT Warangal, they were working on MAF process. So I asked him what is the motive to use MAF process. So he says it is slightly easier to develop and other things. Obviously, that's why. The only thing is that you should have partial knowledge about what are the composition that you use in flexible magnetic abrasive brush. The common things that people normally uses is CIP particles, everybody know. Abrasive particles, everybody know. What is the mixing medium? So people use grease, people use glycerin, people use silicone oil. So as per your requirement, what you use. If you want high viscous, then go for a grease. If you want low viscous, you can go for silicone oil. If you want uniformity and non-stickiness and other things, you can try to use the glycerin and other things. Okay, so you can see here the finishing is you can achieve, but the setup will be very easy if you are going for flat surfaces, but setup will be slightly complicated if whenever you go for the complex features and other things. That is what one has to see. For example, if you see here the variants, you have a flat surface. If I want to do for flat surface or something, this is the one that you have seen in the previous slide. So if we want to go for external cylindrical surfaces, you can see here North Pole and South Pole. Normally always the field of lines travel from North Pole to South Pole. Okay, so this, because of this, there will be a chain formation, and this chain formation and other things will get in upcoming slides. So if at all I want to go for internal surface finishing of any particular surfaces, then you can go for this internal cylindrical surfaces. Okay, so this type of structure you can use for internal surfaces. Recently, we were approached by some industry for doing internal surfaces. However, we have most expertise on abrasive flow finishing process. So we gave the solution in terms of abrasive flow finishing process. Okay. Yeah. So now we are moving toward the how the particles will form. As I said, if you are a beginner, there are multiple types of particles, especially there are two varieties. One is sintered, another one is, you can say, bonded and unbonded. So what do you mean by bonded? Bonded means where you do sintering of abrasive particles onto a CAV particles. Unbonded means where you don't do the sintering. For example, if you see here, the particles are bonded. So sintered basically. You can schematically see iron particle and alumina. This is another area where you can explore the effect of sintered and bonded and unbonded abrasives. Okay. This is the particular paper that where I was one of the authors of this paper, where we checked for MAF on ferromagnetic and non-ferromagnetic. What is the difference? If you see the ferromagnetic workpieces here, what is the thing? If you see the schematic, if you can clearly see the schematics. Sorry that slides are moving here and there because my mouse is having lot of sensors. So the system is Mac system. So if I touch some finger on my mouse, sometimes right and left it will move. So I am not that much acquainted with this. So what I mean to say is that North Pole is at the center. Here North Pole is there, and South Pole, it is like a cylindrical they have given. Okay, so North and South Pole is there. Always field of lines travel from North Pole to South Pole, because of which what will happen, field of lines are moving like this. Okay, since the workpiece is a ferromagnetic workpiece, what will happen, this field of lines are going inside the workpiece and coming. In case of non-ferromagnetic applications or workpieces, this cannot go inside the workpiece. Only this will go from North to South Pole. Okay, in the previous case, it will go inside. Okay. So which is better, which is not better? No, normally if you are, both are approximately same, there is no problem. So people may have some illusion saying that the ferromagnetic materials, the abrasives and other things will stick and other things. So only thing is that you need to play with your composition properly. Now you can see how the flexible magnetic abrasive chains are forming here. Okay. So this is what the, whenever you place a powder onto the workpiece, whenever you switch on the magnetic field, all will form a flexible magnetic abrasive brush or chains. You can see here how the chains are forming. Now you just bring down this and try to do the polishing. In that circumstances, you can see here you have brought down the tool and you are doing the relative motion so that the finishing will take place. Now you can see the surface finish. The best surface finish here is 110 nanometers that is achieved from 580 nanometers. However, in recent days, if you are going to submit this type of 2D plots, people are not accepting because there is no much thing, because no, you are taking at a good region and you are showcasing my surface is very good and other things, but preferably you should go ahead with normally the large area, so that is called SA. So surface area, average surface roughness in a area you have to go. So this particular process can extend towards deburring applications. Deburring is a big issue in terms of whenever you are going to do for ductile materials and other things. Okay, so these ductile materials, if you are seeing that burrs are there on top of it. Okay. What you have to do, you need to remove those parts. That is what one of the most important. So the same setup what you have seen can applicable for deburring applications. So in this case, deburring, this EDM surfaces are there where unremoved molten materials are deposited there. Those things are very complicated to remove. Those things can be removed by magnetic abrasive finishing process. You can see how the recast layer and other things are removed. The second one is magnetorheological abrasive flow finishing process and MRA, rotational also. So in this particular area, Professor Sunil Jha from Delhi and Professor Manas Das from IIT Gauhati work mostly in this area. Acknowledgements to them and acknowledgement to Professor V.K. Jain who shared the slides. Okay, so magnetorheological abrasive flow finishing process is a combination of MRF process and abrasive flow finishing process. That's why we get magnetorheological finishing process. Now you can see here, since we are going to talk about two processes, we initially start with abrasive flow finishing process. So abrasive flow finishing process has multiple things to read, but I am not going to teach you in depth. However, this project or this product is widely used in terms of latest technologies nowadays, because it don't have any constraint with respect to magnetic field or any other thing. Okay, so this completely depend on its own fluid composition and its rheological properties and abrasive properties and other things. The medium normally people uses here is a viscoelastic medium. So why you require viscoelastic medium? So viscoelastic medium will have viscous component as well as elastic component. Viscous component try to move in the direction of applied pressure, and the elastic component tries to move mostly into perpendicular directions. How do we analyze this? For example, oil is a viscous one. You take a coconut oil, just to throw with a hand. What will happen? It moves in the direction where you have imparted the velocity. For example, you take an eraser, you try to press the eraser. What will happen? It will try to bulge dominatingly perpendicular directions. That means that elastic forces are moving into the perpendicular direction. Now, once you know the perpendicular direction and parallel, you take a viscoelastic medium along with abrasive particles. You are applying pressure in this direction, so axial force will be in this direction and axial velocity also will be in this direction. But being an elastic component, it will have a radial component. So this radial component will try to move inside, because of which what will happen is you can shear onto the surface. So these are some of the applications how we do. Just you can watch the animation. Whatever the animation that you have seen is a total knee replacement in a brief view. So the polishing requirements are enormous. At the same time, the curvature from point to point is changing. So most commonly used process is this process of abrasive flow finishing only. Okay, we along with our collaborators from CMTI and other thing is what we have done on establisher socket, knee implant and other things. Okay, these are some of the applications for. This is one of the recent projects that we have received from SCRP on cardiovascular applications for abrasive flow finishing. The second part of MRF process is MRF. So MRF as such, it is a very broad area. Okay, so Dr. Ajay Sidpara from IIT Kharagpur works extensively into MRF process. So those people, if you are interested in MRF, you can contact him. Okay, you can contact us also. We can also kindly can contact, make a contact to him also. There is no problem. हम लोग भी पूछ सकते हैं. So these applications are interlinked basically. How you design the tooling and other things. Okay, so it's as simple as that. For example, if you see, I don't know whether animation, where is the animation? Yeah, so you can see the schematic diagram. We are delivering a nozzle where liquid is flowing because of the magnetic field. It is becoming a rough surface. This is the magnetic is there. You can have two types of magnets. One is permanent magnet, another one is electromagnets. Electromagnets are mostly preferred because you can change the strength of the magnetic field and indirectly you can change the strength of a chain basically. So the strength of the chain means you can do the polishing using different, for example, initially you want high material removal because the surface roughness is too rough, then you can go for high amount of Tesla, like 1 Tesla or 1.5 Tesla or something. As you prolong the surface becoming smooth and smooth, you should be automatically, you have to reduce the magnetic field strength. This variable changing the magnetic field from 1.5 to 1 to 0.75 to 0.5 to 0.2.5 can happen only in electromagnet. It cannot happen in permanent magnet because most of the permanent magnets are having a specified value. For example, 1 Tesla means it will do only 1 Tesla, like that. This is the experimental setup developed at IIT Kanpur under Professor V.K. Jain's guidance. This was developed by Ajay Sidpara. And you can see the zoomed view. For example, the grinding wheel, flexible grinding wheel we have generated here. I worked on this project because PhD after 5 years stipend normally people don't get because of that. So we have to work on additional projects. So you can see here when the magnetic field inside it is occupied, the magnetic field of lines are forming, wherein because of the relative motion and other things, you can see how the brush is deforming or it is upgrading the workpiece. These are the variants, different variants of the MRF process that you can see here. Okay, So another one is ball and MRF process. The expert in this area is Professor Sunil Jha from IIT Delhi. So here the contact area is reduced. For example, if you want to do a knee implant or something, basically the biggest challenge in MRF process, normal MRF process, is that your electromagnet position and other things which lead to the intensity difference or magnetic field intensity difference. If the magnetic field intensity difference is there, the finishing aspects also will change. If the finishing aspect changes, there will be a non-uniform surface roughness onto the surface. For that purpose, people have gone to the ball and MRF process. So this animation, if you can clearly see here, just watch the animation, I will tell you. What you have understood, if you can clearly see here, this is the magnetic field that is coming out. I will take my pen. Once it is going to, you can see the randomly. Yeah, so what I mean to say here is, the fluid is coming out of the nozzle. This fluid, whenever it is experiencing the magnetic field from here, lead lines normally you will see. So what will happen? This randomly mixed material will be systematically doing. Okay, for example, if you see here, magnetic field is there, because of which field of lines are, these are the magnetic field of lines. Then because of the magnetic field of lines, chains are forming. These are CIP particles, and purple color ones are abrasive particles, and this is going to give you a flexible abrasion onto the surface. For example, lens application or any contact lens application and other things. You can clearly see here also the droplet is kept on the workpiece. Whenever you switch on the permanent magnet, this droplet jumped off the workpiece and form a flexible magnetic abrasive brush. Okay. So this is the mechanism. Anyhow, many people know the mechanism, and there was one of the good inventions, I can say, by Professor Sunil Jha and Professor V.K. Jain. So the basic problem in machine finishing is, whenever you try to do initial surface roughness test, so you try to do this. Okay, once you do this, if you try to measure it, for example, measuring it, so you will get a good value, because your tip don't go inside, because lot of material is filled in the it. So if you are increasing number of cycles more, there will be a chance of clearing these particulate materials, beyond which, if you are going to use, what will happen, if you say here, for example, RA is approximately 0.5. It is very difficult to write with mouse. So here it will be 0.25, for example. So here it will be like, so again 0.5 or more than 0.5, because the foreign materials are gone out. So now you need to do the polishing. If you do the polishing, automatically you will get a better surface. So what you can see here, how the nano finishing is happening onto the bulk silicon surfaces. This is the silicon surface, and this. So this is part of the thing that you can clearly see from the MRF process, and practically you can see here how the pen tip is clearly visible onto the finished surface and other things. See, as I said, no, ball and MRF process. Ball and MRF process is patented technology by Sunil Jha and his group. So what is the additional advantage that it can do is, it can do basically a concave, convex, all the things. For example, if whatever you are seeing here, if you see the surface here, this surface has lot of things. One is inclined surface is there, slope, different slopes is there, flat surface is there, concavity is there, convexity is there, and other things. But you want to prove all the concept using the ball and MRF process. And you can see here practically how the finishing is taking place and other things. Okay. This is again magnetological finishing process also can be applicable for the knee implant applications and other things. Hopefully, I think tomorrow Manas may be talking and Professor Manas may talk about MA, MRF in terms of finishing of orthopedic implants, then followed by this tribological aspects and other things from the schedule. I could understand he is a very good friend of me, so he may be talking again on MRF process and other things. You can clearly see here how a knee implant is going to polish. But the basic problem here is to polish this particular component, you may get the surface finish as per your requirement. Whether industries will accept it or not is a big question. In terms of production rate, the biggest challenge is that to polish this, researchers required few days. एंड हमारा इंडस्ट्री के पास इतना वक्त नहीं है, उनको एक दिन में हजारों कंपोनेंट्स निकालना है. So that is a big problem. So how to overcome that? That is the biggest challenge. If I say that my surface is going to give you a nanometer, like 10 nanometers or 5 nanometers or 1 angstrom, very good. If it is the requirement is one component or two component, it's fine. But whenever components are in millions and trillions, or thousands or lakhs of components if you want, if I say that one component will take 7 days or 3 days or 4 days, then people say, okay, bhaiya, aapke paas rakh lijiye aapka technology. Okay, so so new technologies has to be adopted. So the positives about it is going to give you a better surface finish, but the drawback is processing time is very high. At the same time, the non-uniform surface finish you may encounter because the magnetic field strength will vary depend on the freeform surfaces. Okay, so that's why people propose some of the technologies like MRF technology or MRAF technology, where you have seen MRF process and AFF process and move to MRAF process. Now you can see here MRF process and other things. So as I was clearly mentioning you that the fluid is randomly oriented here. This comprises of abrasive particles, CIP particles, which are iron particles. Indirectly, CIP stands for carbonyl iron particles. Whenever it comes into the domain of North Pole to South Pole, there will be a magnetic field of lines wherein you form a CIP particle chain wherein abrasive particles are entrapped. Now, for which you are reciprocating. Now, the same thing practically we want to show you, for which you see this randomly oriented region here when the magnetic field is not applied. Abrasive particle and CIP particles are randomly oriented. But whenever you apply a magnetic field in this region, you can clearly see here that magnetic chains are forming. Magnetic chains are forming and these chains are entrapping the abrasive particles. Now, if whatever the relative motion that you are going to provide will try to polish the surface. You can see here the noteworthy is that initial surface roughness is 280 nanometers, and whenever you are trying to do with respect to 2000 cycles with silicon carbide, if you are going to measure a surface roughness, you are going to get 100 nanometers. Again, if you are going to finish with diamond, you are getting a value of 100 nanometers. Both the value look alike. If you are going with a value, there is no difference between this particular surface and this particular surface. Okay, so but the most important thing is, if you see the surface topography, this is silicon carbide surface topography and this is diamond topography. Even though the value is same, but the topography or morphology is completely different. If you are going to put this particular surface in practical application and this particular surface in practical application, this is one assume that this is 2. So what will happen? 2 will give you better life. That is what. That's why I always want to emphasize to tell you that don't go by RA roughness value or average roughness value or something. You should also look at the surface morphology, for which you can use optical profilometers, or you can have Taylor Robson, Zygo, Bruker, Artec, and Olympus, Zeiss. Many companies have actually. Okay, so why do I know all these companies is because recently we have released the tender for optical surface profilometer. So the problem with respect is the production rate is very less. That's why rotational magnetorealistic abrasive finishing processes came. And this particular process, I am thankful to my friend Dr. Manas Das, who worked into this area. He's currently at IIT Gauhati. So we were both were there at IIT Gauhati, and I moved to IIT Tirupati last 2 years back. So you can see here, it's the surface. Normally it will be good for the flat surfaces as well as it is good for cylindrical surfaces and other things. You can see 16 nanometers. Whenever, if you think about a surface roughness of 16 nanometers and other things, it's a very polished. At the same time, you are not only getting the surface finish, you are also getting cross-hatch patterns. For example, cylinder liner and other applications, you can use these particular surfaces. So again, some of our juniors has worked on magnetorealistic finishing, magnetorealistic abrasive flow finishing on a knee implant. I think Mr. Sarkar and Leeladhar. I think Leeladhar is there in NIT Delhi, I guess. So these people worked on the knee implant and for polishing applications. So there is another area which is hybrid area. Since this particular conference or FDP is also a hybrid, that's why I'm just want to give you a glimpse of hybrid. So chemomechanical magnetorealistic finishing. This particular thing is worked by Dr. Prabhat Ranjan. Dr. Prabhat Ranjan was doing his master's when I was a PhD student, and currently Dr. Prabhat Ranjan is there in Baba Atomic Research Center as a scientist. Okay. Exactly position I don't know, scientist E or scientist D or scientist F or something, but he is a very good friend of mine and he works into this area and he has established a good setup at Baba Atomic Research Center. Those people who want to work on these areas, you can collaborate with Dr. Prabhat Ranjan, and his mentor is there. He is also a very nice person. You can interact. Dr. Or I can say Professor Balasubramanian, Dr. Balasubramanian sir. So you can interact with those people and you can do. So this is one of the fantastic areas that I personally like, because there is a chemical aspect and there is a magnetorealistic aspect and other things. Okay, two advantages of chemomechanical polishing and magnetorealistic polishing, both are emphasized here. You can see here, this is a setup which was used by Prabhat Ranjan in your masters. Just whatever thing that you are using, the physics I am just going to explain you. You are going to add some chemicals to it for passivating the layer. So what is the thing? For example, whenever you try to do the machining operation, normally what you do, you will use a cutting tool much harder than your workpiece material. So the surface roughness that you are going to get is feed marks. So what I mean to say is RA is proportional to F square by 8R. Okay, feed marks is predominating. Why it is predominating? Because your tool is much harder than workpiece material. If I can take a tool material which is lower hardness than workpiece material, then in a conventional point of view, it may not going to work, because assume that I want to cut a HSS steel with copper tool. You cannot cut. That's why what is the thing that you can do is you try to choose some chemical which is going to react with only workpiece material, not to the tool material. For example, you take a silicon. So there are two types of MR fluids are there. One is oil based, another one is water based. For silicon applications, normal water based will be used. So what I mean to say here is that you will, I don't know whether if you're understanding, do let me. If you have, this is my surface. Okay, so the surface has H1 is a hardness. Sorry, H1 is a hardness. So abrasive particle is H2, hardness 2. Okay, so whenever you are treating a chemical with respect to surface, what will happen is you will form a passivating layer. This is passivating layer. So this will have H3. Okay, your H1 will be greater than H2 and greater than H3. So what will happen? So your abrasive particle, which is H2, can only remove H3. That means that active passivating layer. Assume that this is a very rough surface and I want to remove the surface. I am passivating this one by mixing some passivating chemicals or L chemicals. That's why it is called chemomechanical, because the material removal is taking place by mechanical means. So you are going to remove those layers, and your H1 is harder than H2, so it cannot do the finishing process. That means that whatever the surface that you are going to get is the H1 surface, where you don't find any feed marks because your tool or abrasive particle is incapable of scratch that surface. Okay, you can see here how the surface looks like, and you see the surface roughness. Normally it is approximately 10 nanometers. So it is a super polished surfaces. Another thing you can clearly see here how the surface, and as I said, this particular project is between IIT Kanpur and the Baba Atomic Research Center. So Prabhat Ranjan was very fortunate that he is working with Baba Atomic Research Center and he is excelling in this area. You can see the surfaces, these surfaces are predominantly very super polished surfaces. Okay, so the applications, as I said, we have in our lab, as I said, we work mostly into abrasive flow finishing process and other things. So this is one of the setup that we have developed at IIT Tirupati. So it is a commercially developed machine where we have diameter of medium cylinder is approximately more than 150 and other things. Technical details I cannot tell, but this has a one of the nearly smart machine. Only thing is that we don't have some of the sensors. We have some of the sensors to prevent the breakdown and other things. So this is one of the machine that the technology has been given to CMTI, and these are the MOOC courses. Already MOOC courses going on. 1 and 2 is already floated. Many people across the globe are doing. So third one is going to come. Polymer assisted abrasive finishing process is going to come from July to November. So we are welcome to submit various good journals if you are but we are always look for the signs. Don't put with results. Results has to be supported properly. At the same time, it has to be given clear discussion. I mean to say scientific discussions, so that it will be easy for us to accept the paper. Okay, so acknowledgement goes to all the funding agencies. The new thing that we received is, I said, no, 120 crores about TIH. So I started my journey from IIT Guwahati about 5 lakhs, then Bob Atomic Research Center about 23 lakhs, then DST about nearly 1 crore, DRDL about 75, then we received 60 crores from Day-3, which is now called MIT, Ministry of Electronics and Information Technology, where we work on to the theranostics, therapy plus diagnostics for biomedical applications. We have 2 imprint projects with IIT Kanpur and IISc Bangalore, 3 plus 3, which is about 6, then IIT Tirupati about 22.5 startup, then SCRB about 45, and BIRAC, we, as I said, we have received for cardiovascular applications, for heart applications about 40. We have received another one project, which is about 16.8 lakhs from DRDL again. It's a small project. And apart from it, we have another one called a TIH, Technology Incubation Hub on Precision Technologies and Positioning, where 120 crores is from the DST again, where I'm working on one of the vertical called precision manufacturing, since my area of expertise is micro nano manufacturing. So this is in line with the center developed for the lens manufacturing and other things. So I said the most of the acknowledgement goes to Honorable Professor V.K. Jain, because I borrowed some of the slides from him. So I'm very thankful, and I am also thankful for Professor Sunil Jha, Professor Manas Das, Professor Ajay Sidpara, because some of the slides are which are given by Professor Jain are belongs to them, are their work. So, and some of the slides are mine, because I also work partially in this area. Okay, so most importantly, apart from my supervisor, so students, I am just a front face. So these are the students ranging from summer interns to postdoctoral fellows. Currently, my postdoctoral also working with us. So what I want to offer at this particular junction from this particular slide is, we are open for dedicated, hardworking and sincere summer internship students who are going to work with our group. Second, MS external and PhD external. I don't know who for participants. If you are from a government organization, whether it is a research laboratory, whether it is a university or anything, and you should be a regular employee of that one. So you can and make sure that you have some facilities to do research. In that circumstances, we are open for offering you the external PhD and the external MS. So these are the 2 things that we are currently offering. Those people who are interested, they can write to me at this mail IDs. Okay, so again I am saying regular and government, whether it is a state government or central government, not a botheration. You should be, or you should be from a, if you are from a private industry, you should have full-fledged facilities, and you should be having a good rapport in the market. For example, GE, GM or Tata Motors, any big company, those are also we can consider with a special permissions. Okay, so thank you once again for the organizers, and in particular NIT Jalandhar, Department of Mechanical Engineering. I never visited, but I visited through webinar twice. Hopefully we will visit in future. Thank you one and all for your kind patience, and I am ready to accept whatever the queries and suggestions that you have. Thank you.
Definitely, sir. Thank you. Thanks a lot, sir, for this wonderful sharing of the research conducted by you and your research group. So you have covered all the aspects from the domain of magnetic field assisted finishing, the rheological properties, tribological facts, the applications in the domain of prosthetic implants and all. So I hope that our participants are going to be benefited a lot with your the discussions. So dear participant, here I would like to request you all to ask the queries if any. Okay, so you can either ask your queries by directly writing in the chat box, so I can ask directly to sir, or either you can raise your hand so that I can allow you to unmute. Okay, so both are options available for you. So sir, just here we will just wait for 2 to 3 minutes so that the participant can ask some queries.
Yeah, please.
Yeah. Yes. We will just wait for that. Yeah. Thank you. So participants, yeah, I think one participant is there, Desmukh Nilesh. He just raising his hand. So I'm just okay, Nilesh. I'm just making the presenter so allow you. Now you are allowed to unmute.
Hello, thank you, sir.
Yeah, please.
Welcome.
My question is related to
Please
lesser.
introduce yourself. Kindly introduce.
Good afternoon, sir. I am Nilesh Sardeshmukh, working in Pune University.
Where? Pune?
Pune University, I am working in GH Raisoni Engineering College.
Very good. Yeah.
And presently I am a research scholar.
Yeah, please go ahead.
And question is related to the laser surface modification.
which is not part of the presentation. Anyhow, I work.
Yes,
Yeah.
that part you have discussed. That's why I'm interested in that.
Yeah.
So
Please.
in earlier slide you have discussed that you are developing the super hydrophilic surfaces for better cell growth.
Yes.
But there is one more concern that to avoid the bacterial infection, researchers are developing the super hydrophobic surfaces.
Applications are different.
Yes, applications are different.
Yeah, see, so you can develop hydrophilic surfaces, hydrophobic surfaces. Only thing is that you should know what are the input conditions, overlap, and other things, focal point and other things. Okay, so if you are looking for what, first and foremost thing is that what is your application? In that circumstances you have to think. Okay, so anyhow, you please complete your question.
So if the application is related to hip bone, so in that case, to improve the osseointegration,
then you require a philic only, hydrophilic.
Philic only, na? Right.
Yes.
So that is my question. Can you optimize the super hydrophobic and hydrophilic both in this case?
You want to optimize hydrophilic and hydrophobic. Why you want hydrophobic there?
Because many times I have read in the paper that the infection, the failure due to infection is quite large.
That I will come to your question anyhow, definitely. Just I will show you how to overcome your problem. Okay, you don't require their hydrophobic.
Yes, sir.
Why you don't require? I am just showing my slide. Okay, be there.
Yes, sir.
Can you able to see my slide?
Yes, sir.
Yeah. So this is whatever we are developing is a hydrophilic surfaces or super hydrophilic surfaces. Right. So here you said that you want to optimize hydrophobic and hydrophilic. See, normally both are, one is north pole, one is south pole. You cannot optimize both.
Right.
तो दोनों को optimize कर देगा तो neutral आ जाएगा बीच में. Okay, you cannot do that. What you have to do is you can go for hydrophilic. On top of it, you do coating of your material, whatever the bioceramic material that you are coating. Along with the bioceramic material, assume that you are going to have a bacterial growth. For example, bacterial, for example, antifungal is there, or bacteria is there, and many other things are there. Okay, so you know from fluorescence microscopy and other characterizations what type of organisms are growing. Okay, so from this particular study you can understand what is the thing that you are getting apart from the your osteoblast cells, for example.
Okay.
So go back and you try to impregnate or blend those particles. For example, copper nanoparticles or silver nanoparticles. You try to blend along with your ceramic glass particles. For
Okay.
example, then this will act as you have to not play with respect to surface texture here. Your surface texture is constant, super hydrophilic surface, but you have to play with the composition that you are going to coat on the surface. This particular coating, whenever, for example, this particular coating we have done with PVD surface, like PVD coating. Okay, in the PVD RF magnetron sputtering we have done. In RF magnetron sputtering, whenever you want to do a disc, for example, you need to make a target and substrate basically. Okay, so you have to make a disc. So in this case, our disc is hydroxyapatite. For example, you cannot make a 100% hydroxyapatite disc because it is a completely a ceramic and you have to follow the powder metallurgy route. Okay,
Right.
to make a disc. So what we try to do is we try to take some biocompatible materials such as titanium oxide, and we try to add silver nanoparticles, zirconium nanoparticles. We also do for this zinc nanoparticles and other things. What is the advantage of this one is this will act as an antimicrobial. So whatever the growth that is taking place there, you need not to optimize between hydrophobic and hydrophilic, rather than you can take in terms of composition so that your problem can be solved. At the same time, whenever you try to do the sintering operation, silver and other things will also act as some bonding material for ceramics. So that is an additional advantage. For example, if there is a economically, if you want to go, you can go for copper nanoparticles. So copper nanoparticles will act as a binder and your disc will be in a formidable state actually. So my suggestion would be you need not to, for the application of hydrophobic surfaces is completely different,
Right.
where you don't require any coatings or something. Whenever you don't want contact of these microorganisms, in that circumstances you require hydrophobic. But here you go with hydrophilic or super hydrophilic with change in your composition of your coating. That may suits you. That may be my personal suggestion to you.
Yes, sir. Yes, sir. Okay, thank you. And in concern with sir, if I do different wettability surfaces
Mm.
and without adding any composition
Mm.
for different textures,
Mm.
uh, can I check for the growth of cell, osteoblast cell?
Could you repeat again?
For different wettability,
So
specific
you are texturing the surface.
in case of texturing, right? So without
Okay.
adding any composition. So
Okay. So
for
you want to check on the bare surface with the texturing
yes, and
without coating.
yes, and willing to find out the optimization of cell growth for which wettability surface.
So on what is your workpiece material?
Titanium.
Yeah. So now I will answer your question because we have done this work and our paper is under review. Okay. So we have done this work on ultra fast lasers on titanium. So we have done. We don't want to do texturing. We don't want to do coating. Just we want to understand on the titanium what is happening in titanium. Titanium is a low thermal conductivity material. At the same time, it is a highly reactive material.
Yes.
In that circumstances, always you have an oxide formation. Since you are going to texture using laser, even though you maintain lot of stringent environment, you will have a oxide formation. Okay. So
Yes.
titanium oxide is a biocompatible material and you will get a growth. But here you may get bacteria, virus and other things. That is the basic problem because you are texturing if it is a since you want to grow osteoblast cells or any other bone cells, for example, I'm telling about bone applications, you don't have any other compositions which counter the microbial. So there will be a chance of certain percentage of microbials. So you have to go here also super hydrophilic surfaces only because cells has to adhere properly.
Yes.
But microbials will be there.
Okay.
I don't know whether I answered 100% to your question.
And what will be the major challenge then in this regard, as per you,
Major challenge is
for my study in this case?
no. I don't know what is your study. What is your study? I don't know. See, you asked me 2 questions. I answered 2 questions.
Yes, sir. Yes.
If you can tell me what is your study, I can tell you suggestion.
Yes, sir. My study is laser surface texturing
Yes.
for enhancing the biocompatibility of orthopedic implants.
Okay. So, as such, you cannot use directly a textured surface. Okay, until unless, see, you have to see the market trend.
Yes.
So, okay, you may get a degree, PhD degree, that is different story. Okay, you may get a publication, that is a different story. But texturing followed by cell culture, you may have some drawbacks of these microbials. Okay, at least you go for a nano coating of any other materials like okay, so for example, if you don't have a coating facility, I understand some of the institute may don't have the coating facilities. In that circumstances, you just go for texturing different texturings. You wettability anyhow you can measure because goniometer is there, contact angle measurements are there, and you can optimize the texturing or the texture dimensions, depth and width, overlap, as you have seen in the this one, overlap, 25% overlap, 50% overlap and other things. You can play a major role on top of it, and you can say this particular texture, which is still a superhydrophobic or superhydrophilic or hydrophilic, will suit, and you can say that you minimize the microbial growth. You understood what I mean to say?
Yes. Yes.
Okay, which texture is going to minimize the microbial growth? See, osteoblast cells may adhere properly to some surfaces.
Yes.
Microbial cells will adhere. See, आपको तो रोटी पसंद है, मेरे को चावल पसंद है, सिंपल लॉजिक है ना? मेरे को सफेद कपड़ा या लाल कपड़ा पसंद है, आपको ब्लैक कपड़ा पसंद है. Okay, your taste is different, my taste is different. So similarly, these organisms also will have their own adhesion ability towards different surfaces. So the adhesion ability of the osteoblast cells is different. Adhesion ability of your and microbials are different. In microbials, you have multiple microbials. Virus hai, fungus hai, bacteria hai, lot of things are there.
Yes.
Okay, so in that way, just only thing is that you need to do a lot of fluorescence study by giving multiple dye colors or colors, multiple colors. So you need to differentiate which is bacteria, which is virus, and which is fungus and other things. So yeah, that is what my suggestion. You can play with respect to dimensions, depth and width and other things. Okay.
Yes.
Okay. Please.
Thank you so much, sir.
Yes, sir. Very much. Thank you, sir, for your guidelines.
Sir,
Tell
one
me.
more participant is there, E. Naveen.
Yeah.
E. Naveen, I think you can hear me. I'm just making you the presenter, so you can unmute yourself.
1 minute, मैं 5 minutes की कॉल करता हूँ मैडम. Tell me.
I have just made you the presenter. Okay, you can unmute if you are there.
Hello.
Sir.
Yes, Naveen, you are audible. Yes.
Sir, good evening, sir. Naveen from Sri Sairam Engineering College, Chennai, sir.
Yeah, please.
Sir, there are some other finishing techniques like the plasma-assisted polishing and the laser-assisted polishing. So while polishing, after the polishing, the surfaces which are polished may have some heat-affected zone, no, sir. So
yes.
How to overcome that, sir? The plasma-assisted polish, especially these two polishing techniques.
Which polishing technique you have at your institute?
No, sir. We don't have, but I have read after the plasma-assisted polishing and the laser-assisted polishing techniques.
Okay. So you need to characterize. There will be a elemental change will be there. For example,
yes, sir. Microstructure change will be there after the polishing.
Yeah. No, no, after polishing nahi hai. So whenever you use thermal source to polish,
Okay, sir.
automatically you cannot avoid some things because that is the basic things
Okay, sir.
like recast layer, heat affected zone and conversion layer. These are basically common. Only thing is that you can play with respect to the post processing techniques. For example, if you take a plasma polishing technique or a laser polishing technique, you take a simple laser polishing. The laser polishing also will have a heat or thermally destroyed layer. So you need to check the composition, or what I mean to say elemental composition, and accordingly you have to go for any type of lapping or any other normally non-chemical polishing techniques. If you ask me particularly what is you can use any abrasive technique where there is no chemical.
Okay, sir.
For example, magnetoroyological finishing process without chemical you can use to polish. If it is a flat surface or it is a regular surface. If okay,
Okay, sir. And sir, if I'm asking if any irregular surfaces are there, how to overcome that, sir?
irregular surfaces, see, you have to manipulate, or you have to manipulate means you have to fabricate a converse shape of the magnet. Otherwise, you
Okay.
cannot do by MRF process or MAF process or something.
So only for the standard shape you have done.
Can you repeat your question, please?
Sir, only for the as far as the previous lecture concerned. So only for the some regular shaped component only you have done like that only, sir.
So I just said no. For example, I will just show you what is the drawback. Where is that? Can you see my slide?
Yes, sir. Yes, sir.
Where is this? Yeah, knee implant. Where is the knee implant? Yeah, right. Yeah. If you see here, see my north pole is here. Can you clearly see what is
Yes,
the
sir. Yes, sir. Yes,
basic
sir.
problem of MRF and magnetoroid? My north pole is here. My south pole is here. I am having a knee implant with a curvature like this. Okay. So my poles are fixed. You are getting my point?
Yes, sir. Yes, sir. Yes, sir.
So the distance between this, can you able to see my arrows?
Yes, sir. Yes, sir.
And the distance between this is variable. Am I right?
Yes,
So
sir.
the magnetic field intensity here will be H1. Here it will be H2 or B1, B2, whatever you may think. So magnetic field intensity H1 will be higher compared to H2 because the distance from the magnetic. अरे कहाँ है यार? चला गया. Yeah. Okay. So the distance is variable here, because of which the magnetic field intensity will be different. This magnetic field intensity, if it is different, the finishing also will be different. So what I mean to say is that you will get a better surface here, you may not get better surface here.
Okay, sir. Okay.
Because my magnetic field intensity will be function of the distance. Okay, it may be easy to show this particular thing, very colorful and very shining, but how do you know what is the roughness here and what is the roughness here? Until
Yes,
unless
sir.
they specify it, that is a basic problem. So for a free-form surfaces and other things, in my view, it is slightly difficult, but you know, but is very dangerous in English. Okay, But if it is within the range of the customer acceptance, there is no problem.
Okay, sir.
Okay, for example, here it is 0.2. Assume that here 0.5. So if the customer is happy with 0.5, he will be always happy with 0.2 also.
Yes, sir. Yes, sir.
Okay, because you are getting a better value there. Now the question here is whether the cells or the body fluids flow on this one, because you need to place inside the human. So body fluid flow velocities will be different. If here roughness is different, here roughness is different. So there will be a tingling action inside the body. That is what my literature says.
Okay, sir. Okay, sir.
For to overcome this, very conventional process is there. Our advanced process is there called abrasive flow finishing process. There you can partially overcome because there is no interference of this magnetic field. However, there also what you can say is that you need to change your fixturing. If you don't change your fixturing, then again the same problem will be there because your entrapping region is very less. Okay, because the distance is very less. If the distance is very less, what will happen? The interacting forces will be very high. So for this, fixturing is very easy. There is no problem. Only thing is that you take a knee implant and you go in the EDM process and you just dump it, die sinking EDM. So you will get a converse shape. That's all. So you divide into two parts. You cut this knee implant into two parts. You take a flat surface. For example, this is not a north pole. It is a flat surface. You go and do a die sinking here. What will happen? You will get a converse shape like this. Am I right?
Yes, sir. Yes, sir.
Here also you will get a converse shape like this. So now you place it. So what will happen? You will have an equidistance. But in the case of magnetic field, but the problem is you need to get this type of complex magnetic is very difficult.
Okay, sir.
So magnet banana mushkil hai. I don't know whether you understand or Hindi or not. Magnet is.
Yes, sir. Yes, sir.
Yeah. So that is what the worry that I have always on magnetic field assisted finishing process.
Okay.
But however, every process has its own pros and cons. This process, if at all you want the best process, the best advantage of this process is you can control the forces. Whatever the forces that you want, you can control by magnetic field. That is the best about this particular process.
Thank you, sir.
Nobody is 100% perfect, na? So I am also, you are also. So you have your own positives and negatives. I have my own positives and negatives. And Ravi Pratap Singh has his own positives and negatives.
Exactly,
Okay.
sir, you're right.
Yeah.
Yeah, exactly the same thing actually being asked by another participant. He's just saying the same about the magnets, that can we design the magnet according to the desired shape of the workpiece?
You can design costly.
Yeah. Exactly. Okay, so I think Mohit Agrawal, you got your.
बना नहीं सकते हैं, हम लोग बना नहीं सकते हो, बाहर से मंगाना पड़ेगा.
You can design, but the formation
डिजाइन देना पड़ेगा बाहर लोग को जो बनाते हैं. So I don't know who makes it because this is not
exactly.
my primary area.
Actually, it's not the domain of research exactly
my
for
area, but there are people in China who makes it, but currently situation is not good, so you may not get. And then you can get from European countries and US. You may get. So if you want the details of this design and other things, you can contact Dr. Manas Das, or tomorrow morning I think is Dr. Manas Das.
Definitely Professor Manas will be there, sir.
This question you can pose to our beloved Dr. Manas Das. He may answer in a better way.
Definitely, sir. So thank you. Thanks a lot, sir, for this much the wonderful discussion over the magnetic field assisted finishing and its application in the industrial domain, and this much elaborated queries and their responses. So it's really was a nice guest, sir, to have you over here, sir, in this particular talk. So it was all our pleasure to have you for this session. Thanks a lot, sir. Thank you so much.
Thank you.
So dear participant, it is done for today. So all the 3 sessions are being done now. Okay, so we will meet tomorrow sharp at 10 a.m. So Professor Manas Das from IIT Guwahati will deliver his talk. Okay, so we will meet at 10 a.m. tomorrow. Thank
So
you.
you are not recording these lectures?
It is available on YouTube actually. So we are just streaming it live, not recording. Sir.
Okay. So if I want to listen,
yeah, exactly. I will share the links. Actually, Atal Academy asked the YouTube links. That's why we are doing that.
Okay, so
yeah.
Can you share so that I will?
Definitely.
So whatever the already completed वाला भी मैं देख सकता हूँ ना?
Exactly. It is there, sir. It is there.
Okay.
I will send you the links also.
Yeah. Thank you.
Thank you so much, sir.
तो अलग-अलग का अलग-अलग link है क्या?
Yes, sir. Day by day actually it get varied.
नहीं, day by day is okay, but मतलब मान लीजिए कि पुलक मोहन पांडे सर का एक लेक्चर है।
नहीं सर, नहीं कंप्लीट डे का है, कंप्लीट डे का
एक दिन का एक लिंक है।
Yes, sir. Yes.
Okay, very good.
I will share it.
ठीक है।
Thank you so much. Okay, dear participant, thank you. Now you can leave, please. Okay.
Yeah, if you have any queries, still I'm happy to.
Yeah, you can even write to me, so I can forward your queries to Professor M. Ravi Shankar, sir. Okay, so as you can see that how much the elaborative response he's just saying. Okay, he's just giving that so much nice response, even solving all the queries over here. So it's nice learning for you all, even for me. Okay, so thank you so much, sir.
ठीक है, okay. चलिए, convey my regards to all the colleagues.
Hope to see you. I will do.
Hope to see you and Aviral को भी. Aviral क्या है? Aviral है क्या?
I will pay. Aviral is in room, sir. Actually, I think having some lab and all.
Okay.
Yeah. I will pay your regards.
Thank you.
Yeah. Thanks a lot, sir.
Yeah, I'm leaving now.
Yeah. Please, sir. Thank you. Okay, dear participant, you can leave now. Thank you.